I'm going to talk about some upcoming work with Alan Fang and Jimbo Wan about some wave decay on slowly rotating extremal Kerr-Newman. And I want to already put out a disclaimer. This is the first time I give a talk about this topic, and it's also the first time ever I give a Blackboard talk. So this is just to put the expectations, set the expectations very low, so that anything that is better than an a total disaster is a good thing for me. So just had to say. Okay, and the reason why I'm finally giving a Blackboard talk, because I don't have to write all those long and terrible equations about that come out of the Einstein equation, because I'm only going to write, in fact, one equation, which is the scalar linear wave equation. Okay, so this is what I'm talking about today. And so here we're looking at this equation for where G is, so really the topic will be, my talk, I will talk about extremal Kerr-Newman. Okay, so you may have heard already of Kerr-Newman. I'm going to just say a few words. So this is a 3-parameter family. Of solutions to the Einstein-Maxwell equation. This is Einstein-Maxwell equations. The 3 parameters are the mass, the angular momentum, and the charge. I'm going to call them M, A, and E. So this is a solution to the Einstein-Maxwell equation. So it represents a rotating charged black hole. And if you have seen Kerr, I guess you all have seen, because Mihalis wrote the metric yesterday. I guess there is if you slightly change the way he wrote the metric, and you can write the metric of Kerr with only writing delta, and the capital delta and the R squared plus A squared, something like that, then Kerr-Newman will really be, you don't even see that it's different from Kerr. You just, as long as you add into the delta also this extra parameter plus E squared. I guess if you start writing down, the M, then okay, you may see some differences. But if you write down the Kerr metric, you can think in the delta, you plug in this expression with this extra E. And then, of course, you don't plug the E wherever there was the A in other parts of the coefficients. Then you'll see that this is not the solution to the Einstein vacuum equation, it's the Einstein-Maxwell equation. And we have a black hole, so we're only interested in really black holes when there is a relation between these parameters. Right? So the relation is that A, right here, A squared plus E squared is less equal than M squared. Okay, so this is the condition to have an event horizon. And now the extremal case is really when this condition is saturated, so that E squared plus E squared is equal to M squared. So then the difference really with Kerr becomes even smaller, because then the delta in this case is really just R minus M squared, which is the same thing you would have in the extremal Kerr or extremal Rice-Nordstrom. In fact, let me already mention here that this 3-parameter family contains all the subcases that we are familiar with. So if E is equal to 0, you recover Kerr. If A is equal to 0, you recover Rice-Nordstrom. If both are 0, you recover Schwarzschild. So this is kind of contains them all. And of course, similar in the extremal case. So in the extremal case, if E is equal to 0, you pick up extremal Kerr. If A is equal to 0, you pick up extremal Rice-Nordstrom. Okay, of course, there is no extremal Schwarzschild. So this is kind of the general picture of the Kerr-Newman family. Now, so what do we know about this equation in this metric? Well, we know a lot. And so what we know, and here I'm going to separate into the two cases, the sub-extremal and the extremal case, right? So really in the sub-extremal case, we really know a lot. This was a lot of work that also Mihalis mentioned yesterday in the past 20 years or so from the community. Mathematical General Relativity really looked at this problem in this family of solutions, and I'm going to summarize all the results, saying that we have what are called energy, what I would call Morawitz, and redshift, and RP estimates. So these are estimates on, if you can think of them as a priori estimates on the solution of an equation like that. And energy estimates will be something like that will tell you, that's what Mihalis showed yesterday, how to derive them in the case of Schwarzschild, right? So there will be some control on some positive combination of derivatives on a space-like hypersurface of your solution in terms of the initial data. What I would call Morawitz are really some similar estimates that instead of controlling just an integral over a space-like hypersurface, they control an integral over a space-time region controlled by initial data. Redshift, again, is what Mihalis mentioned yesterday. It's an additional estimate that gives extra control close to the event horizon in the sub-extremal black holes. And RP is also some additional estimates. Both the redshift and RP were introduced by Fermo-Soloniaski, and this allows really to pick up the behavior in the asymptotically flat end, because all these black holes, of course, are asymptotically flat. So we kind of have all these things that in the years have been, discovered and built. I can possibly write all the names. I'm going to just write, some. Again, as I already mentioned, the Fermo-Soloniaski. I mentioned Tataru, Ganu, Anderson Blue, and then the definitive result is the Fermo-Soloniaski Schlapentov-Rothman, really to obtain these results for the full sub-extremal case in Kerr. There's also work by Sivin to extend it to Kerr-Newman. Basically, kind of this work can extend it to Kerr-Newman in sort of similar fashion. Who works in Kerr, who work in Kerr-Newman. Okay, so this is kind of the picture of sub-extremal. So I would summarize as good. It's it's very good. Okay, so then what about the extremal case? Okay, so the extremal case, of course, some things change because we are in Toronto, so we all know that in the extremal case, there are some things that happen that did not happen in the extremal case, which are in particular the first thing to mention is a conservation law. And so there is a conservation law on the event horizon that roughly says that the dr, so this is in going Huntington-Finkelstein coordinates, so it's like the transversal derivative. An object like this is conserved along the event horizon. So this also, it implies that the higher derivative of this will blow up along the event horizon, roughly. The k derivative will blow up as k-1. So you see, for example, the second transversal derivative will blow up. And this, of course, is the Areta-case instability. This was found by Stefanos, and this was 2011, and some subsequent work. So this again is he first found in extremal Rice-Nordström, but then it's very general. In fact, follow-up work. You can see that this actually holds in extremal Kerr. It holds in a very general case of extremal horizons. So you have this conservation law, but nevertheless, apart from what happens here at the event horizon, in fact, what also Stefanos was able to prove is that, say, outside the event horizon, pretty much what you had before. You can kind of prove what you had before, with the exception of the redshift, that it's you don't have that anymore. So what he proves is that in the case of, again, extremal Rice-Nordström or extremal Kerr in axial symmetry, you actually had again, let me just summarize it this way. So you can prove energy, Morawitz, RP estimates. So you do get, I should also say, as a consequence of all this, you can actually also prove pointwise decay for the solution. And so that's what again Stefanos 2011, 2012 proved that even though you have this conservation law, this instability, you can still do many of the things that you were doing in the sub-extremal case. Now, what about the extremal Kerr in its more let's say outside axial symmetry? So the first work is actually the work of Rita that proves mode stability. So in extremal Kerr, so this is, I think this was 2020. She proved that the solution to this equation actually proves something more general, like the solution to the Tokowski equation, but in particular, the wave equation is a Tokowski equation for of spin 0. You do have more stability, so there is no exponential growing modes to this equation. So this is really in the case the full case of extremal Kerr with no symmetry, and then there is some recent work of Dayan in extremal Kerr for the M modes solutions of this equation. That what Dayan showed is that they present an even worse instability that what happened in the case of what Stefanos showed. So it's something that again roughly was something like k to the -1/2. So you see that already at the first derivative can blow us up along the event horizon. It asymptotically blows up. And also this is a gauge instability. Okay, so this is that's a nice name, I think. So this is roughly the picture in the extremal case, and really for the scalar wave equation. There have been many other works that, for example, looked at precise asymptotics of solutions to the wave equations. This was work of Stefanos, Dayan, and Yannis to look really at kind of the price law. I mean, Jan talked a little bit about this yesterday. Then there are works. They also extended on some of these works to nonlinear wave equations, like semi-linear, quasi-linear, satisfying null condition, and so on. So there have been many follow-up works. Of course, Dayan also talked about the charge scalar field, which is a more complicated picture because it will be a little bit more complicated equation in the case of extremal Rice and Nordstrom, for which she is able to also do this kind of things, deriving those estimates. And then, of course, there's many more exciting development about extremal black holes. I think we'll hear more with Mihaly's talks about the fact that extremal black holes can arise dynamically in finite time, and so this is all somewhat related to the extremal black holes picture. But let me not go into that. I'm really sticking to the scalar wave equation, the most possible boring, most boring situation, right, that you can think of. But you see, still, we're still kind of lacking somewhat the full picture in the case of extremal, which is fine. It means there's more to do. Okay, so let me immediately then state the theorem that I want to talk about. Hopefully, I'll try to only use this half of the board. Okay, so the theorem, as I said, is joint work with Allen Fang and Jimbo 1, and this is, as I said, hopefully coming out in the next month or so. So I'll state it very simply. After this introduction, I would say that solutions, what we prove is that solutions to this equation on here. Okay, this is on extremal Kerr-Newman, right? And then we need to restrict our solution to the slowly rotating case. Let's say if you're a pessimist, you say, oh, this is slowly rotating extremal. If you're an optimist, you say this is a strongly charged extremal. Okay. So of course, we can be optimist the whole time. As all pessimists would say, they are realists, right? They're not really pessimists. They just look at how things are. So we will just say slowly rotating. But obviously, there is an equality that has to be true. If one of the things, there's a sum of two squares is equal to something. If one of the two is small, the other one is large. Okay, so that is kind of the picture that we have. But really, of course, we're gonna exploit a lot of things that come from the slowly rotating. But there are the same features that come in the strongly charged, meaning in the Rice-Nordstrom case. But nevertheless, we are rotating, so we're really outside spherical symmetry in this picture. Well, those solutions satisfy those estimates. Okay, so they satisfy. So we write energy, Morawitz, and then here I have Rp and R minus M to the minus P estimates. So these are weighted estimates at the event horizon. So these were introduced by Stefanos, Dejan, and Yannis in one of their many works on the extremal case, and they're used ever since in the extremal picture. And they really are the symmetric kind of weighted estimates from the null infinity. And I'm going to spend most of the talk talking about these two things. So I'll just bear with me here, because I'm really going to focus on those, because those I think are the most interesting aspects of this problem. But really, what I want to say is that whatever we said it was good, it's good in this case with no symmetry. So there is no symmetry assumptions here. And just to make things a little bit more down to earth, whatever down to earth a math talk can be, I'll just also say in particular what is the pointwise decay that we get, just so that we have something to stare at. So the L infinity norm of my psi will be bounded by some initial energy that it will be some higher order initial energy, and then we'll have something that looks like this. So here delta is just a small number. It's in fact a small number that is related to the angular momentum. It's related to the A over M. So this, so what is this tau? So already, okay, let me try to draw here. So hopefully that's fine for the. Okay, so here, if this is my Penrose, my Penrose diagram of the exterior region. I'm only talking about the exterior region here. So just if you think about a foliation that does something like this, so this will be my sigma tau. I'm really thinking of deriving these estimates in a region like this. Okay, so this I have some foliation that really ends at the event horizon and a null infinity. If you're in a Rice-Nordstrom, you can really think of having u equal constant, b equal constant. Here you have to kind of adjust it a little bit, but it doesn't really matter. So with a time foliation like this, what we get, you see, it's a time decay which roughly goes like time to 1/2. And this I will already let me already stress that this is non-optimal. In fact, there's no claim that nothing that we do is optimal. This is really basically kind of the first attempt to get these estimates. This is not sharp, but it also it looks like very much not sharp in the sense that I guess there is. I'm not so sure how clear is the expectation of the decay, but let's say in the sub-extremal case you will have t to the 1. There is some. I would expect this should be higher, right? This should be t to the 1. Let's say maybe 1 minus something that depends on the A, and maybe it could go, because you see if A is equal to 0, we are in the Rice-Nordstrom picture, and there we know that it should decay like t to the 1. So this is non-sharp, but nevertheless, at least it's something, and it's as I said, the result that at least doesn't have any. We don't have any. You don't need to assume any symmetry on the solution. So, are there any questions about the state? Yes. No, this delta is not is actual delta. So this vanishes. So it vanishes towards the event horizon. yeah, the radiation field will decay very. Yes. Yeah, so the radiation field, yeah, will, yeah. Yeah. But I think this is consistent, this would be consistent with, sorry? I mean, sorry, what was the?
So there's two deltas that are canceling each other out.
No, this goes like one. Oh, yeah. Sorry, yes. Yeah. Sorry, I say yes. Yeah, exactly. Yeah, sorry. The event horizon, this one vanishes, yes. Vanishing at the event horizon. Sorry? It depends. I mean, it all goes back to this initial data. I mean, basically the initial data that you, I mean, if we have some initial, the initial data assumption is, I mean, you have, in the fact that this initial data is finite, it's similarly to the fact that you need to assume some decay of your initial data to deal with the asymptotically flat case, something like, r squared psi goes to 0 at the initial data as r goes to infinity. Something similar will come up of the fact that this initial data is finite at time 0. It's yes, it is vanishing identically. But if you assume that this initial data is finite, then this solution will be will vanish identically. Yeah. Yes.
Is there any restriction of P?
So the P, so in the regional picture here, P is really between 0 and 2. And I'm going to say a little bit more here what you mean. No, but yeah, but again, going back to this thing. So this is, so let's say this is the pointwise decay that you will get out of the first, the first application of these estimates. Then what you can do, you can do something better than this. You can run.
So if you take a psi that could be identically 0 near the event horizon initially, but it's not 0 somewhere else, then some of it will go to the event horizon. Right?
Yes. Yes.
How can you stay 0 on the event horizon forever? Is a feature that's dramatic.
This is okay. Now I'm getting getting confused about this. Sorry. Yeah, it's R equal M. Yeah, no, it is still R equal M. Yeah, the event horizon is still R equal M. Yeah, this, I mean, for the initial, I mean, I'm happy to say maybe more details about what is the initial data, but really, the initial data that you have here, I mean, in doing, when you run through the argument and you kind of do, I mean, in the final step, really, when you do the pointwise estimates, the kind of the Sobolev embedding, then you pick up this. There is this factor that comes up. Yeah, but maybe we can try to say more about this later. Okay, so let's say this let me already get out of the way some parts of the proof. So in particular, if A over M is much smaller than 1, which is really our situation, then the we are in a simplified setting, because now what we have that the so let me draw some of the important regions here. So this will be my near horizon region. Then I will have some near sky region. Okay, and then I will have some. Let me see if I have another color. And then there will be some trapping region. And you see the way I drew them is already clear that those things are separated between them. And this is because we're looking at the slowly rotating case. Okay, in a slowly rotating case, the trapping is concentrated close to R equal to M, which is the trapping upper surface in the extremal Rice and Nordstrom. And sorry, this should be near sky. And also the super radiance will be somewhere in here, somewhere inside the near horizon region. So these two things are kind of separated. This means that these two parts, energy and Morawitz, are also kind of can sort of be kind of separated. So trapping region is really wherever you will find some null geodesics that is trapped so that it's orbital. So it's yeah, no, that was R is constant. And so yeah, this will be very close to R equal to M. Okay, so the fact that the super radiance, for example, is separate from trapping, it means that I can construct some, let's say, cutoff time-like, globally time-like vector field that is killing everywhere except, a small region that is not in the super radiance, not even at trapping. And so this allows me to pretty much handle the energy case kind of separately from Morawitz. And the Morawitz, for those of you who know, so these will be obtained with some radial vector fields. And in fact, we are in very slow rotating case, allows us to use, there are various things that one can use. The thing that we use is like some pseudo differential correction of some differential multiplier that would work, for example, in extremal rest and Nordstrom, and this is really alla Tataro-Toyano. Okay, so this, and really the fact that this if A is small, the fact that you're living really in extremal black hole doesn't really affect these issues at all, pretty much, because if you have a slow rotating, you can find this globally time-like vector field that is killing almost everywhere outside the important regions. And you can find this pseudo-differential correction that for small a really works just in the same way as it would work from passing from Schwarzschild to slowly rotating Kerr. It works here in the same way. So I'm not going to say, I don't want to say much about this. Okay, so let me instead talk about more like the other parts of the proof, like the RP and R minus MTP, which is where the difference with the extremal horizon Nordstrom actually come up. And for this, I will try to, let me try to use these two blackboards to compare these two cases. Okay, because there are two boundaries to our space-time, right? Okay, so the first one is the event horizon, R equal M, and the second one is R equal infinity. Okay, so let me then define some boundary defining function for those. So this is obviously when R minus M is equal to 0. So I'm going to call it rho H. And this is when rho scri is equal to 0, where rho scri is 1 over R. Okay? So I'm trying to put it on the same footing the two boundaries. Try to see really how they differ in my context. Okay, so now I need to use some coordinates that are well adapted to this picture, and of course we have them. Those are the Eddington-Finkelstein coordinates. In one case, I will have the ingoing Eddington-Finkelstein coordinates. Okay, let me write this. They both use the tortoise coordinate. Looks like this, and then you will have some phi, which I think is so here I'm changing coordinates from the Boyle linguistic coordinates, which I didn't write down the metric, but okay, I'll assume you can imagine what they are. You as long as you change the phi and you write V as T plus R star, you get now the expression of the metric that is now regular at the event horizon. You can do the same thing here for the outgoing Eddington-Finkelstein. The tortoise R star is the same. Phi needs to be changed. And then you have U, which is T minus R star. Okay? So this is, you have your new set of coordinates. In fact, you can think of having as your new coordinates are actually v rho h theta phi. Okay, actually phi star, but I will forget the phi the star probably. And then here you can use as coordinates u rho scri theta and phi. Okay, so instead of r, you can use r minus m or 1 over r. Okay, these are kind of your new coordinates. So let me write down what is the metric in actually going to write down the inverse metric, which is more useful than the metric to understand the wave equation. So this is okay. There's this factor. The metric, the inverse metric in Goen-Eddington-Finkelstein is given by, let me see if I can remember. It's some dv plus a d phi d rho h, and then I'll write it already. So let me write it. Let me write it first with the DDR. Okay, it's okay. DDR and DD rho h is the same, but and now here I think it comes with a delta. Yes, so delta dr square dv. Okay, so this is what the metric, the inverse metric looks like in ingoing Eddington-Finkelstein coordinates. And now in outgoing Eddington-Finkelstein, this is, it's the same with the minus sign in the first piece. So it's the u, the r, and then also there is a delta dr square plus d theta. Okay, so this is really just to say, to explicitly show that these two the coordinates adapted to the two boundaries of my spacetime, they look very similar to each other, right? So there is this event horizon and null infinity, they kind of are kind of a little bit symmetric, and I can make it even more explicit if I use, instead of DDR, I use my boundary defining functions as coordinates. So then in that case, I can see by by a chain rule, right? I can write that d rho h is equal to the dr in ingoing Eddington-Finkelstein. The dr in outgoing Eddington-Finkelstein is minus r square dr in the outgoing Eddington-Finkelstein. I think if I can do my my chain rule correctly. No, in fact, it's actually -2. Sorry, it's d rho. Okay, sorry, I wrote it the other way. So it's d rho I. So again, by doing the chain rule, so this in particular says that r dr is equal to minus rho scri d rho scri. And so then we can use this to write my wave operator. Okay, so again, the wave operator will look very similar. To write down the wave operator, you use the inverse metric. So let's try to write it. We have my box, and here I will get precisely this piece, this r squared plus a squared dv d phi d rho h, and then I will actually have some rho h d rho h squared plus Laplacian on S2, and then here this gives me some a squared sine squared theta dv squared, and then I have some 2a dv d phi, and then there may be some first order terms in a dd rho. And then in here, if I try to do the same thing here, I will see that I get again something very similar in these coordinates. So now the minus sign here, as disappear, is actually the same sign because it's absorbed by this minus sign from here. I get something like 2 r squared plus du plus a over r squared d phi d rho I, and then it's also very similar rho I d rho I squared plus Laplacian plus this a squared sine squared theta du d phi. Okay. Yes, hopefully you can see. Okay, so now the metric kind of looks again for some sort of first order terms. And I also want to notice at this point that in fact the moment I define this vector field, it's actually natural to it's natural to consider vector fields that are tangent to my boundary. And those are what in B calculus are called B derivatives. So this in my case, really the ones that are tangent to the boundary, it will be some rho h, d rho h, and then dv, d theta, and d phi. Same thing here. I will have something that is rho scri, d rho scri, du, d theta, d phi. Okay, so these are what I would call B derivatives. Again, kind of using the terminology that comes from B calculus. It really simply means those are the derivatives. They span, all the derivatives are tangent to the boundary. Okay, so then I can notice that most of my operator, my wave operator, is made of B derivatives. In particular, the stationary part of my operator, which really would be this piece. Okay, even this whole piece is actually made of B derivatives. So these are all derivatives that are tangent to the boundary, right? Because you see, this comes as rho with the rho d rho. So this, in fact, it's tangent because it vanishes at the boundary, right? But while d rho doesn't. So this is tangent. This is tangent. Dv is tangent. Dv d phi are tangent. And same thing on this part. So in fact, this is it's a second order B operator. And this will mean, and as I will see now, I'll see in a second, how one derives these weighted estimates. It is by using some weighted expression of these B derivatives. And in fact, those B derivatives act very well with this kind of operator. It kind of goes through. So the difficulties really will come from this first piece. The first piece is where you see the difference with Rice and Nordstrom, as I will say now in a second. Okay, so let's say now, okay, this is the metric. So how do we do the estimates? Okay, how do we do RP estimate? Let me start with RP estimates because probably are the ones that most people are more familiar with. So how do we do RP estimates? So to the RP estimates, we're looking at a region that is very close to null infinity. Okay, so you should think in this region, rho scri is very small. Okay, so rho scri is now our kind of smallness, but we can choose rho scri to be as small as we want by pushing it ourselves very close to null infinity. So to do RP estimates, we will use as a multiplier some r to the p minus 2 dr of the outgoing Eddington-Finkelstein. If you don't know what does it mean to use a multiplier, you can really think of taking the wave equation, multiply by this x applied to psi and integrate by parts. In fact, that's what some people may be a bit confused by the p minus 2, because if you try to do this by integration by parts directly, you would multiply by r to the p, just because there is an r square in the volume form that you're not writing down if you by integration by parts directly. This would actually be the multiplier. So what is this in terms of our DD rho? I mean, this is again it's a simple change of variable. I can write this. I can save if I write it r to the p minus 3 and then write it as r dr. Then I can write this as my rho scri 3 minus p, and then r dr is actually just a minus rho i d rho I. So this becomes a 4 minus p d rho I. It doesn't matter too much, just to show that again it's a weighted version of my B derivative that is tangent to the boundary. And in particular, this vector field is of course transversal to null infinity. Okay, so this is what you will do there in the r minus m minus p estimates. Now the picture, we are in the close to null infinity, close to the event horizon. And now here the multiplier will also be, now okay, you want to point it towards the event horizon, so it will have a minus sign. right? Like, so it will be, let's say this is minus DDR or minus D rho H. So you will have, again, minus R minus M, P minus 2 D dr. Okay, I may get some of the yeah, no, of course it's 2, yeah, it should be 2 minus P, okay, and then this is minus rho H 2 minus P d rho H. Again, just a weighted version of those derivatives. So what does this allow you to give? Well, for, let's say in the case, let me start with the RP. For P between 0 and 2, you get something like you get some integral on the region where your rho is very small. Okay, so on some fixed, if you want, some fixed region, you get some control of some rho to the gamma of your B derivative, right? So this will be some rho. I'm gonna write just as rho, and then let me just write the angular part. So this is, if you do it directly in this way, you'll get this is bounded by some initial data, which is also weighted. Okay, so this is in the case of, because of this numerology that I have here, this corresponds to having gamma to be 4 minus P. So you have some control on those derivatives. So you see you're missing some derivatives. You can actually add the, let's say the du or dv. I'm going to use this also for that other board. But you're going to, you can add these two derivatives by adding as a multiplier something that is transversal. So if you add some large constant, for example, of a transversal derivative, so something like this, or something, this looks a little bit like the T energy, you're kind of adding a T energy to control also the remaining derivatives. But really, this is a kind of weighted, this is a kind of some again, B weighted in the sense that it contains all derivatives are tangent to the boundary and weighted with a common rho to some power gamma. For the RP, so this again, this was done in extremal Rice and Nordstrom. So you get the same thing. So I'm not going to rewrite it because again, just by write as rho, you will write rho H because it's really kind of you get the same expression very close to your rho equal to 0. You will get something that looks like this. In that case, because of the numerology here, you will get the gamma should be I think should be 2 minus P in that case. No, sorry, it should be. So okay, I got it wrong. So this should be 3 and it should be 1. Okay. Again, I think most people maybe either used to do this in double null coordinates, but if you do it in outgoing additive Finkelstein, you see that this is kind of the power that comes up. Okay, so why do these things work? How do we and why is in our case different? So let's look at Minkowski. In the case of Minkowski, our operator will just reduce to R squared box equal to, now you see there, if A is equal to 0, you just get 2 du d phi, sorry, du d rho scry, plus something that is again, I'm going to just write it, it's a B operator in the sense that it only has things that are already tangent to the boundary. So when you do the multiplier in this kind of integration by parts, you will naturally pick up something that looks like this, that is written in terms of derivatives that are tangent to the boundary. So the only one that is not is this one. Why it is not? Because I have a du and a d rho I. D rho I that is not tangent to the boundary. Only it's rho I d rho I that is tangent to the boundary. So and this is kind of the right way of dealing with this. One way, for example, the simplest way is to use the radiation field to kind of get rid of this term and being able to nevertheless prove this kind of estimate. Now let's look at the case of extremal, even like again extremal Kerr-Newman for RP. What do I get in extremal Kerr-Newman? I have my prefactor of box, and now this is also going to be, as we said, a differential, some sort of B operator that doesn't give me problem. Now, what about this term? I'll have the term that comes from Minkowski, right? So the 2 du d rho I. So this is okay. I'll be able to deal with it just like I did in Minkowski. And then the extra terms are a over r squared du d rho I. So if I write it as a, forget even about the a, like I write it as 1 over r times 1 over r. So 1 over r is my rho scri. And then I have du rho scri d rho scri. So again, I recreated two derivatives that are tangent to the boundary, but I have this extra factor, and then everything else is again given in terms of derivative that are tangent to the boundary. So in particular, I have this extra factor, and I'm in a region when rho scri is very, very small. So this is really a lower order term with respect to this. So because again, you don't even use the smallness of the a. I mean, there's nothing with smallness of the a. This is really just rho I is very, very small. So this extra factor, it's kind of can be dealt even, you know, it's even better than whatever is left, whatever is the stationary part of your wave operator. So this is why the RP work for P between 0 and 2 in all asymptotically flat black holes, right? Because really Kerr-Newman or even extremal Kerr-Newman is asymptotically Minkowski S cry. Okay, now let's go to this other board. Okay, so let's look at extremal Reisen-Nordstrom first. Okay, so this again what was done by Jan and Stefanos and Yannis. Okay, so let's look at what happens here in Reisen-Nordstrom. So A equals 0, I get R squared box, and then I get 2 R squared dV d rho h plus again my you know B operator, my things that are already tangent to the boundary. But now I see this term. Don't be fooled by the R square. R square is like a constant now because we are very close to the event horizon. So this is now really it looks exactly like this term in Minkowski. Okay, so and this is because and it's even more. Really this is because extremal Reisen-Nordstrom is the event horizon of extremal Reisen-Nordstrom is symmetric to its asymptotic end, and this is something that also encoded in the Koch-Torrance symmetry that is between the extremal event horizon and null infinity. So whatever you were doing in Minkowski, you can kind of do it here. I mean, of course, you still have to do it, but you can see that the structure is the same. Okay, now let's look at extremal Kerr or Kerr-Newman, for that matter. Now, in that case, we have, that prefactor. Now you can see that really what I'm left with is this extra term. I have, whatever I had from Reisen-Nordstrom, right, d rho h. And then whatever is left is dv d rho h plus a d phi d rho h. Now this term doesn't come with a smallness factor anymore. It's really not like here where I had this a over r squared that was helping me because I'm in a R very large regime. Here, this is just as big as this term. Even for small a, this is O1. I mean, this is O1 near the event horizon. This is O1 near rho h, very, very small. I cannot just make myself closer and closer to the event horizon to control this term. There is something about the a that appears. And in fact, that's what we see. So and let me summarize it here, saying that extremal Kerr-Newman is not asymptotically extremal Reisen-Nordstrom at its event horizon. Okay. So it was Minkowski it was asymptotically Minkowski near null infinity. It's not asymptotically extremal Reisen-Nordstrom. Yes, thank you. Near at the event horizon. So this is kind of where we start to realize that we cannot expect the same hierarchy that goes on in the extremal Reisen-Nordstrom to smoothly go through in this case. And in fact, what we have is, right, as a proposition, for A over M less than 1/2, and again, this is it's a bound that comes out of the computation. I don't really have a, I think there is more to understand, and I don't expect any of this to be sharp. But in this bound, we do so we have R minus M to the minus P estimates. So these bounds will hold for P that is between 4a squared over m squared and 2 minus 4a squared over m squared. Okay, so you see here, if a is equal to 0, you recover the region p between 0 and 2. And maybe I should say, the p between 0 and 2 comes out of the coefficients, whatever coefficients come up here, that, in order for this to be positive, you want this bound to be true. Now, if a is equal to 0, you see you recover the case in extremal rise to Nordstrom. But as gay, so in particular, if a over m is 1/2, right, this becomes quarter and so forth. So p becomes squeezed into 1, basically. So there is no hierarchy anymore. There is only one member of the family. At least, this is, again, this is what we have. That I want to stress again. This is not. I'm not claiming that this is the final thing. So this, so why? So I want to really kind of come back to the theorem that we had, in particular to this time decay, so that we have this truncated time decay. It is related to an issue that it comes from this, because we think of this estimate as some degenerate redshift estimate. So this is it can be interpreted as some sort of degenerate redshift estimate, and that's where this restriction comes into play. So let me, in the last 5 minutes, give some sort of sketch of the proof of the theorem. So we actually start with a choice of there is some choice of multiplier in axial symmetry. So this is something that we had with Jimbo maybe a couple of years ago. So in the case of extremal Kerr, but kind of redoing what Stefanos did in back in the days in physical space. So there is a choice in axial symmetry, actually works for all A. That will give you something like this. So you have some divergence of some current that controls, you have some coefficient of your dr in Boyer linguistic coordinates. Then you have some coefficient for your angular and dt derivative, and then you have something else for the 0 order term. Okay. So then in axial symmetry, this is what you would get. But if you're not in axial symmetry, there is some extra term that looks something like this, dt d phi. Okay. So this is you can, there are various ways to cook up a choice like that. We do it in a certain way. But you see this extra term now, modulo correcting the fact that this cannot, you have to correct it, the pseudo differential operator at trapping, blah, blah. Again, I don't want to get into, but this extra term really, let's say outside trapping, the small a let you deal with this, because you have this smallness constant in front, and you have these two derivatives that are fine outside trapping, but this is actually degenerate, right, at trapping. And because of how trapping is in extremal Kerr-Newman, if you take the geodesic potential and you take the derivative, that's how you get the trapping, that will also vanish at the event horizon. So this will also degenerate at the event horizon. So you will have a factor here, r minus m. So this is 0 at the event horizon. So now you see here then okay, if you're near Scry, this actually decays very fast in R. So it's fine. You have a very fast decay in R. You don't even need the smallness of A. if you are near the event horizon, now this is the problem, because now this is, even for small a, this is again O1 at the event horizon, doesn't have any degeneracy at the event horizon. The thing you would like to absorb it by degenerates at the event horizon. So the smallness of a is not really gonna help you here. So what helps you is this R minus MP estimates. So we need to use one member. It's really one member of the hierarchy to close our Moravec estimates. So which member it is? It's a member that gives us, I think it's the one that comes with 1, gamma is 1 plus delta. So I wrote earlier that gamma had to be, 2. So gamma, so here you had gamma is like 1 minus p. So we take p, I meant p to be 1 plus delta. So then here you see you pick up something, some rho h to the minus delta. And then you have your derivatives. And so now you see that this factor is big, because it's a rho to the negative power minus delta. Yes, I'm finishing. So this is big. So this is what allows you to absorb the error term, and you don't need again the smallness of a, because now this is big in its own right, and that term is now smaller because it's only O1. This is all rho to the minus delta at the event horizon. So if you get closer and closer to the event horizon, there will be a point where this will be larger, and so this is what we do. But now we have used really one member of the hierarchy to close Moravec. This means that when we have our closed Moravec, so that's good. But now when we want to enhance the weights of Moravec, and we add back the hierarchies, we only have whatever is stronger than this that is left, because the weaker are going to be absorbed by the one we already added. So then we're only left with the 1 plus delta with half of the range of my p. And that's why, in the standard process, to go from whatever your RP, your weighted estimates, you get pointwise decays. That's why you get only t to the minus 1/2. So this is kind of the what gives us decision. Again, I don't expect any of this to be sharp, but okay. But I'm kind of convinced that this term is there. Because again, this term comes from the geodesic potential. There's not so much you can do about it. Maybe there are some refinement you can do near the event horizon that are allowed to change that. But we don't know yet. But yeah, this is one way of getting around it. At least you get some decay, which may hopefully be improved at a certain point. But yeah, this is all I want to say. Thank you for your attention.
All right, so hello everyone. I'm Kumar. Right now, postdoc at Institute. First, I'm going to send competitors to UMass for this talk. Today, I'm going to talk about some linear and nonlinear.
Is that okay?
Yes.
Okay. Today, I'm going to talk about linear and nonlinear phenomena in black holes. Binary black hole coalescence is likely the most violent astrophysical process that can trigger rich linear and nonlinear phenomena in black hole spacetime. After a decade since the first event, GW 150914, we have detected hundreds of gravitational waves from merging binary black holes. For a typical system, there are 3 stages involved, including inspiral part, merger part, and the random part. And so far, numerical relativity still remains the only first principle approach to track the whole evolution process and to produce accurate gravitational waves. But nevertheless, people have developed some analytic tools, such as post-Newtonian theory and black hole perturbation theory, to gain some physical insights into different dynamical regimes. Especially the random part corresponds to the oscillation of the remnant black hole, And the emitted gravitational wave is largely consistent with the superposition of the so-called quasi-normal modes, whose complex frequencies are determined by the mass and spin of the remnant to the no-here theorem. And in the following, my discussions will be rooted in this perturbative perspective. I will be covering two major aspects, the nonlinear part and the linear part. For the nonlinear portion, I will specifically talk about mode coupling and dynamical nonlinearities. All right, so let's get started. Feel free to stop me anytime if you have any questions. Quadratic quasi-normal modes are likely the simplest objects that reflect the nonlinear features of general relativity. In short, it is a second-order effect of a quasi-normal mode. Let's here imagine a linear mode H goes as e to minus omega t. This mode carries energy and orbital angular momentum, which can lead to an effective stress energy tensor and further perturb the space-time geometry. And roughly speaking, its source is given by h squared. So we can imagine that the space-time will undergo a driven oscillation at 2 omega. And the amplitude is proportional to a squared. The coefficient in front of it, which we refer to as the excitation factor, capture the intrinsic nonlinear features of a Kerr black hole. Why do we care about quadratic quasi-normal modes? First, like I mentioned, they are the nonlinear features of general relativity, but maybe they are simple enough that we can develop analytic tools to handle them. This is in sharp contrast to some other general nonlinearities, such as the merger part of binary black hole merger. In that case, we have to rely on numerical relativity and treat it as a black box. There is no available analytic tool. And finally, although the quadratic modes are sourced nonlinearly, they still enter the gravitational wave in the same way as those linear quasi-normal modes. So there is no need to design new analysis tools to study them. We can just rely on some existing quasi-normal mode fitting methods. By using a black hole second-order perturbation theory, we found that for a single quasi-normal mode, it can be sourced by some multiple channels. This diagram shows the simplest one. So imagine we have two linear parent modes, omega 1 and omega 2. Their coupling can lead to this summed frequency, omega 1 plus omega 2. But this is not the end of story. The subtlety, there are a few other channels which are more subtle. The subtlety comes from that for a given quasi-normal mode, it is always accompanied with a mirrored frequency channel. Here, for example, let's imagine we have a psi4 contains a single quasi-normal mode. And in its metric data, h mu nu, because this is a real number, it has two frequency components. The first one is the original one, and the first one is its complex conjugate. So this second one is called the mirrored channel. So here, let's imagine we have the third parent mode, psi minus 2 bar, whose frequency is at minus omega 2 bar. Here, this bar means complex conjugate. Notice that this psi minus 2 bar is a different parent mode from psi 2. Itself represents an independent quasi-normal mode. Because of this mirrored channel, psi minus 2 bar can generate a frequency component in its metric at omega 2, which can couple with the first quasi-normal mode omega 1 and leads to the excitation of the same quadratic mode. And similarly, we can exchange the rho between 1 and 2, and this brings us to the third channel. And finally, we have the coupling between those two barred modes. So in the end, for a given quadratic mode, it is sourced by 4 channels, and there are 4 parent modes involved. Oh, sorry. Based on this, we can formulate, sort of formulate some Feynman rules in the sense that the quadratic mode amplitude can be written as a coupling constant multiplied by the corresponding parent mode amplitude. For example, in this case, this channel can lead to a quadratic mode with amplitude given by this constant C++ multiplied amplitude of omega 1 and omega 2. For the remaining 3 channels, we have parent modes which belong to the mirrored branch. So we need to first take complex conjugate first. For example, in this case, this minus omega 2 amplitude is given by A minus 2. We need to first take a bar for that. And whenever we do this, we use a minus sign in the subscript to track this operation. So in the end, we have plus, minus, plus, and minus 4 channels. Putting all those 4 channels together, the total quadratic amplitude is given by the sum of all of them. So here, as you can see, those 4 coupling constants are really the fundamental quantities that reflect the nonlinear features or nonlinear responses of a Kerr black hole. So it would be interesting to compute them from the first principle. Here, to achieve this goal, we adopt the black hole second-order perturbation theory. The whole calculation steps are quite involved. So instead, here I just want to give overall. I just want to highlight the overall workflow. So imagine we have a linear quaternion mode represented by this well scalar psi4. Then we can construct the corresponding Hertz potential. Then working within the auto radiation gauge, we can do the metric reconstruction to construct all the metric components for this quaternion mode. Then using the commutation relations and Ricci identities, we can build the quantities in the Newman-Peierls formalisms. Then with all those established variables, we can extract the full source term for the second order Tokosky equation. And finally, we just solve this equation to obtain those coupling coefficients. It turns out that those coupling coefficients, they depend only on the dimensionless spin of the black hole. And remarkably, we found that this minus channel always vanishes, regardless of chi and the choice of the parent modes we pick. At the beginning, we found this behavior fully numerically, and very recently, we are using, with the help of AI, we are able to confer this analytically, but we still don't know whether there is any deeper physical reason or deeper physical symmetry behind it that make this constant always vanishes.
In some sense, there is nothing special between plus and minus. If I change my convention, how do I define this relative harmonic? So it is one of the two of these here, right?
No, actually, no. So imagine you have a single mode. This mirrored channel is always special, right? So this is not present in psi4. Sure. So you always have a special component. Yeah, right. But again, this number always vanishes. We don't know whether there's any deeper reason. Apart from this first principle calculation, there is a complementary strategy which is fully data-driven. So in this case, we can send a Gaussian gravitational packet into a black hole and then evolve the system using full 3+1 numerical relativity. Then we can measure the gravitational waves at future null infinity to extract all those coupling coefficients. So both methods should give consistent results, and indeed they do. So in this figure, this gray curve, this gray curve is the analytic result that we computed with black hole second order perturbation theory as a function of black hole's dimensionless spin chi from 0 all the way to 1. And meanwhile, those scattered points with error bars, they are measured from those numerical experiments. So you can see that they are both of them agree, both of them are consistent, and they follow the same spin dependence. So actually, this example gives a good this comparison gives a good example to demonstrate the success of black hole second-order perturbation theory. All right, so that's a basic picture for the quadratic quasi-normal mode. Let's take a step back and reveal the physical insight behind this. Schematically, the black hole dynamics is given by the Tokosky equation driven by a nonlinear source. And importantly, the left-hand side is identical to the linear operator. So the whole nonlinear effects completely enter through this nonlinear source term. Here we can think of this source as a tidal field acting on the black hole, and the corresponding particular solution can be thought of as the tidal response, which is related to the tidal field by a sort of through a set of quote-unquote Wilson coefficients. And here we can compare this pattern with the quadratic quasi-normal mode that I introduced. And apparently you can see that those coefficients that I mentioned earlier, they are basically the nonlinear Wilson coefficients of a Kerr black hole. From this perspective, quadratic quasi-normal mode, it is an adiabatic nonlinearity in the sense that once we provide a pair of parent modes in terms of their amplitudes, the following tidal response is fully determined by those constants. So they don't have their own dynamics. So based on this, in parallel of this adiabatic nonlinearity, as we can imagine, there has to be other class of nonlinearity which is supposed to be more dynamical. This is similar to dynamical tide in neutron star or in exoplanets. So this dynamical response can be triggered when the time scale of the tidal field matches the intrinsic time scales of the system. And in this case, the response is no longer adiabatic. Instead, they can have their own dynamics. The resonance is one good example. Let's consider one example. Let's consider a toy model. This is the example that Niels used yesterday. So here we have a Tokosky operator with a nonlinear source. And in the initial data, we can set it to be a pure 2-to-0 quasi-normal mode. And because of this nonlinear source, it can generate a frequency component whose value is very close to the first overtone 2-to-1. This plot shows the relative error between this frequency component and the 2-to-1. And as you can see, the relative error is always on the order of a few percent, and it vanishes in the extremal limit. So here, as you can imagine, the 2-to-1 first overtone can be resonantly excited by this fundamental mode through this nonlinear coupling. The second example is the parametric resonance. Let's imagine we have some nonlinearity, and this nonlinearity introduce some time-dependent dependence to the background. And when this time scale matches the black hole quasi-normal mode frequencies, there could be parametric resonance. And the examples are given by Yang and collaborators back in 2015. And finally, I would like to highlight other class of dynamical response, which is called traveling wave resonance. This resonance is by nature very different from the first mode resonance. In the first case, we need to have resonance when the driven frequency matches some internal eigenfrequencies of the system. However, there is no such requirement in the traveling wave resonance. Let's again consider a toy model. This is a plane wave. This is a 1D plane wave, a 1D wave equation driven by a traveling wave. And its particular solution is given by t times e2 I omega times t minus x. So this t factor says that this wave equation is always resonantly excited. And very importantly, here you can see the left. This flat spacetime doesn't have any internal eigenfrequencies. And so as a result, this omega can take any real value. Here we can understand this feature by borrowing some insights from field theory. In that case, each spatial location will have a local harmonic oscillator, and those oscillators talk to each other through this spatial derivative. In the presence of this traveling wave, it can coherently trigger the excitation of those neighboring harmonic oscillators and lead to a cumulative growth in psi. So those are a few examples for the dynamical nonlinearity in black hole spacetime. Below, I'm going to show you how to use numerical relativity to reveal some of these dynamical nonlinearities. As we know, in the literature, the most common approach to accept nonlinear phenomenon in black hole spacetime is to establish some initial data containing some gravitational packets, and then we can send this packet into a black hole to trigger some nonlinear phenomenon. But this approach has some caveats. First, we always need to solve the constraint equations to construct the initial data. This can be subtle and it can be difficult when this pulse is strong enough. And second, this packet is always spatially compact. As a result, the pulse always triggers a transient effect. The nonlinear interaction always happens within the scattering timescale. And after that timescale, the system quickly transitions to the linear rain-down stage. So for our purposes, we would like the nonlinearity to happen over a longer timescale. This is something that initial data itself cannot really handle. So to fix this, we design an alternative strategy to study this. So instead of using initial data, we change boundary conditions such that we can inject gravitational waves into a system. And in our setup, we can specify this gravitational wave to be any function of t and time and the spatial coordinates at the boundary without introducing any constraint violation. As a result, we can actually change those gravitational waves when the simulation proceeds. For example, we can inject a gravitational wave for some time, then turn it off and then turn it back on after a while. Or we can inject continuous gravitational waves into a system. This is analogous with using a spoon to keep stirring a bottle of water. When the fluid is driven continuously, some nonlinear mechanisms behind that could trigger energy cascades across scales and generate small eddies due to this direct turbulent cascade. Here we hope that the same intuition could apply to the gravity scenario as well. If we continue to use the gravitational wave to stir a spacetime, maybe some nonlinearity could build up and lead to some interesting phenomena. This is our numerical setup. Here we shoot a continuous wave into a Schwarzschild black hole at a far distance. We do this by specifying the well-scalar psi4 at the outer boundary. Here, this psi4 is decomposed into the spin-weighted spherical harmonics and multiplied by a time-dependent function. And in our case, we just set it to be a monochromatic sinusoidal wave. And in each experiment, we fix the angular pattern as well as the frequency value. And finally, we monitor the dynamics on the apparent horizon. Okay, so the first obvious nonlinear phenomenon that we saw is the frequency-dependent mass accretion. This plot, this top panel, shows how a black hole mass changes with time. Let's first look at this dark blue curve. In this case, we can see that the mass grows linearly in time, which implies that the black hole enters a steady accretion state. The accretion rate m dot is proportional to the injection amplitude squared. And the coefficient in front of it is frequency dependent. This frequency dependence arises because the transmissivity of the black hole potential barrier depends on the frequency. Because we are injecting gravitational wave at a far distance, and it needs to penetrate this potential barrier in order to be accreted. That's how this frequency dependence kicks in. Now let's go back to this figure again. In this panel, it shows the transmissivity as a function of omega times m. In the low frequency range, you can see the transmissivity is almost 0. And it gradually, the black hole becomes gradually transparent when omega goes to a larger value, and eventually it asymptotes to unity. So as a result, we can look at this. We can look at this light blue curve. This is especially interesting. At the beginning, we inject a wave at a low frequency. So the transmissivity of the system is quite low. And you can see that the black hole barely accretes mass. But over time, this black hole becomes a little bit large. Then the effective frequency seen by this black hole, which is controlled by omega times m, this combination becomes bigger. Then the system transitions to the high transmissivity regime, and it becomes more efficient for the black hole to observe the energy. So eventually you can see that the accretion slope becomes bigger than its initial stage. In our most nonlinear setup, this black hole can become 6 times bigger. All right, so now let's take a look at the response on the apparent horizon. In this setup, we set this gravitational wave to be a monochromatic wave with 2-0 angular pattern. This wave can trigger a bunch of responses on the apparent horizon. Here, this plot shows each angular and frequency component as a function of time. In the top panel, we have the first order linear response. This is the omega component in the 2-0 harmonic. And we have confirmed that its profile scales with the injection amplitude A. So indeed, it's the first order effect. At the second order, we have 2 omega in the 4-0 harmonic. And this is analogous with the quadratic personal mode that I introduced. Again, we confirm that its profile scales with A squared. And finally, we found 2 third-order components in 6-0 harmonic, including omega and 3 omega. Both of their amplitudes scale with A cube. Schematically, this omega is equal to omega plus omega minus omega, and the 3 omega is equal to the sum of 3 omegas. So far, those excitations are quite typical nonlinearities that we are familiar with. They are adiabatic in the sense that once they are excited, they just stay here. They don't develop additional dynamics, and their amplitudes are completely fixed by A to some power multiplied by some constants. However, if we repeat this experiment with bigger and bigger injection amplitude, something much more interesting could happen. Here, this plot shows the evolution of a few frequency and angular components as a function of time. Here we have a few injection amplitudes as indicated by the different colors. For weak driving, for example, in this case, once the modes are excited, they just stay here, right? So they just stay here. But when A increases, we can see that those modes undergo the secondary excitation, followed by saturation and a decline. So we always see this feature in in all those modes. The bigger the injection amplitude we choose, the earlier this secondary excitation happens. We found that the growth rate scales with A cube, and the saturation amplitude scales with A to the first power. those excitations are by nature very different from the early adiabatic responses, because in this case, those modes have their own dynamics. They can exchange energy between each other, can have this growth, saturation, and then a decline. So they are adiabatic responses. To better see this, we can look at this time frequency plot. And again, let's focus on the response in the 6-0 harmonic. At the very beginning, we have the excitation. We have two third-order modes excited. So we have 1 omega and 3 omega. And after some time, this 2 omega is excited, and then it's saturated and goes away. And then after a while, this omega undergoes a similar dynamics. If we use this yellow dashed arrow to connect all those 3 stages, we can see a very clear pattern. Here, this 3 omega behaves as a major energy budget to fit the excitation of the following frequency components. And here we can see that the underlying nonlinear mechanisms features an inverse cascade. The coupling tends to transfer the energy inversely down to lower frequencies. We also see similar responses in 4-0 and 2-0 harmonics. As for the 4-0 on the left, we have the dominant excitation initially at 2 omega. This is analogous with the quadratic quasi-normal mode. And after some time, this omega is excited. And we can, again, rely on the intuition that we have. This omega behaves as a major energy budget to source the following excitation in omega component. And finally, in the 2-0 harmonic, we have this first-order response at omega. But in this case, there is no available lower frequency slots for the energy to cascade. So this component just stays here and gradually decays away. So far, I have focused on Schwarzschild spacetime. If the black hole has a spin, the story could become a little bit different. Let's again look at the response in the 6-0 harmonic. Remember that in the Schwarzschild case, we have 2 dominant third-order modes, omega and 3 omega. Because in this case, 3 omega is stronger than omega, it can become the major energy budget to trigger the following excitations. However, when black hole has a spin, let's see 0.7, omega actually becomes bigger than 3 omega. Then in this case, 3 omega stops to behave as a major energy source. And for the omega, because there is no available lower frequency components for the energy to flow, it just stays here and goes away. There is no available, there is no subsequent secondary excitations anymore. Okay, so that's the basic story when we inject 6-0 harmonics, 6-0 gravitational waves. I think the major takeaway message is that the nonlinear mechanisms in general relativity tend to transfer the energy inversely down to lower frequencies. Then this raises an interesting question. How about the angular part? Could we observe similar dynamics as well? So to study this, we inject 6-0 gravitational waves into a spacetime. And again, we see a bunch of mode excitation. In the 6-0 harmonic, we have this omega component, which arises as a first-order effect. Its amplitude scales with A. And we also have this second-order mode, 2 omega, which comes from the second-order coupling. Its amplitude scales with A squared. We also found this 2 omega in 2-0 harmonic and 4-0 harmonic. Both of them are second-order effect. And as you can see from those black curves, once those modes are excited, they just stay here without undergoing additional dynamics. So they are adiabatic. But more interestingly, we can see that there is also omega component excited in 2, 0 and 4, 0. Their amplitude grows linearly in time, and the slope is proportional to a cube. So it implies that the omega component undergoes third order resonance. And more interestingly, we found that we also found similar nonlinear resonance in flat spacetime. So this implies that this resonance is not tied to any eigenfrequencies of the system. So this aligns quite well with the traveling wave resonance that I introduced earlier. You know, in the presence of a traveling wave, we can have this resonant solution. Finally, this plot is the mode amplitude as a function of angular harmonic measured at different times. The darker blue means later time. So this is our injection. Initially, they have comparable amplitude, but because of this nonlinear resonance, their amplitude grow linearly in time, and eventually they become bigger, stronger than this injected amplitude. And so we can see that the gravity also tends to transfer energy down to larger angular structure. So that concludes the first part of the talk, which is about nonlinearity. Before moving on, is there any question? Quick question. If not, okay. So let's move on to the second part, which is about some linear response in black hole spacetime. To begin with, let's recall the numerical setup that I used to study these dynamical nonlinearities. In this case, we modify boundary conditions to inject gravitational waves into our simulation domain. In fact, this methodology is a part of a bigger topic in numerical relativity. As we know, the most common approach in numerical relativity to solve Einstein's field equations is to adopt this Cauchy approach. The basic idea is to split the spacetime into three-dimensional spatial slices as a one-dimensional time direction. As the name implies, we can convert the system to a Cauchy problem by providing some initial data on the first slice and some boundary conditions. We can evolve the metric data forward in time, step by step. For example, in this case, we can put two black holes in an orbit on the first slice and numerically evolve the system to let them in spiral and merge and emit gravitational waves. At the outer boundary, gravitational waves are mainly outgoing. So people normally pick transparent boundary condition to avoid reflection at the boundary. But is that sufficient? The answer is no. It's not sufficient for general setup. To give you an idea, let's consider a toy model. Here we have a binary black hole system on the left, and this is our outer boundary. As the system evolves, it emits gravitational waves outward. Some gravitational waves that have already passed through the outer boundary can be reflected by the local spacetime curvature and re-enter the simulation domain again. Right now, this transparent boundary condition is not able to capture this backscattered effect. So in order to really simulate this inner region in an exact manner, we really need to prescribe how this backscatter wave evolve over time. It turns out that this is a very hard problem. So right now, people just ignore this piece from current simulations. Luckily, this backscatter effect decays very quickly with the outer boundary. So in principle, one can put this outer boundary far enough to avoid this problem. But this is really a stopgap solution. It only works for some short simulations, and it makes the simulation unnecessarily expensive. So in order to fix this issue from the first principle, we really need to design a different formulation to handle the outer wave zone in order to predict the backscattered gravitational wave. So far, there are a few formulations in numerical relativity, including the Cauchy evolution, which can handle the near zone, the characteristic evolution, which is suitable for the wave zone, and meanwhile, there are a few formulations which can handle both zones simultaneously. And for our purposes, we could just use this characteristic evolution to compute the backscattered effect. The basic idea of the characteristic evolution is to adopt different slices for evolving Einstein's field equations. Slices mean observers. Those Cauchy slices correspond to time-like observers who sit at different spatial locations, and they are synchronized by those space-like hypersurfaces. And during a simulation, we track each observer and see how the metric data evolve with the local time. However, for the characteristic evolution, we instead formulate the space-time using those null rays generated by outgoing null radiation. So here you can, as you can imagine, this is more suitable for radiation propagation. Those observers are organized by those null slices, and the simulation marches toward this direction. By using those null slices, one can rewrite the Einstein's field equations using a bounded X coordinate system, which brings us to the so-called characteristic formulation, which we can use to handle the dynamics in the wave zone. So in practice, we can put both Cauchy and characteristic systems together to handle both near zone and the wave zone simultaneously. And in this setup, we sent outgoing modes from Cauchy to characteristic to evolve the outer wave zone on a single time slice. Once this is done, we can send the backscattered modes from characteristic to Cauchy to construct the exact boundary condition, including the backscattering waves. In other words, we match those two systems together and evolve them at the same pace. So this method is called Cauchy characteristic matching, or CCM. And here you can see that an important step to achieve CCM is to inject the backscattered radiation as computed from the characteristic side into the Cauchy side. And this is exactly the tool that I used to study this dynamical nonlinearity. So after my years of development, right now this CCM has become a quite mature method, and we can use CCM to merge binary black holes quite routinely. And below, I'm going to show you an important application of CCM, which is to review late-time power law tails. As we know, those tails come from the backscattering of gravitational waves of large-scale space-time curvature. So if we want an algorithm to pick this infrared structure, we really need this algorithm to cover the entire simulation domain. And this is exactly what CCM is good at. So in this example, I use CCM to merge a binary black hole system whose parameters are chosen to be consistent with the first gravitational wave event, GW150914. This is the psi4 as a function of retarded time extracted at future null infinity. Apparently, you can see a very clean tail at late time. And this is, in fact, the first time we are able to run CCM on BBH mergers, and we are able to resolve tails in the fully nonlinear regime. If we do not use CCM, we will instead get this blue curve. So in this case, we can see that there is a huge systematic error at late times, and those errors are completely caused by the wrong boundary conditions because they are gone if we push the outer boundary far enough. Right. So, but you see, the CCM is able to pick up the correct tail even when the outer boundary is close, very close to the system. All right, so that's the basic story for CCM and the tail. Is there any questions so far? Yeah. The decay rate is around -3.5-ish in Psi4. Here L is equals to 2. We can chat more of that. Okay, so the final part is about the near horizon source-driven emission. As I have mentioned a few times, the black hole dynamics are governed by this Tolkowski equation with a source term. A useful approach to obtain this solution is to use the green function method. So the total solution is given by the green function convoluted with the source term. Here, as a result, as you can see, the total waveform is contributed not only by the green function, including quasi-normal modes and the tail. There is also a piece contributed by the source term. And I believe Laura will also talk about this in her talk. Especially when this source moves very close to horizon, there will be some interesting imprints on the gravitational waves. So let's imagine we have a small particle gradually falls into a central black hole along this black trajectory. At the early in-spiral stage, it triggers gravitational waves directly toward observers. So this regime can be described by the post-Newtonian theory. Once the black hole, once this particle gets close to the photon ring, quasi-normal modes are excited. But this is not the end of story. Even during and after this regime, this small particle still continues to behave as a source to trigger the source-driven emission. You know, this source-driven emission from the very early in-spiral stage all the way up to the very late stage, they should evolve continuously. It is not shut down abruptly. Here I use those gray arrows to indicate this near horizon source-driven emission. Because they are sourced very close to the horizon, they actually carry some near horizon features. There are two important features that we need to consider, including the fringe juggling effect and the redshift effect. As we know, when the central black hole rotates, it can push the nearby spacetime to push the nearby to drive the nearby spacetime and push the particle to co-rotate with it. As a result, the emitted source-driven emission should oscillate at some frequencies to reflect this fringe juggling effect. And meanwhile, once this wave is sourced, it needs to climb the potential barrier in order to escape to infinity. That's where this redshift effect kicks in. And this redshift effect makes the wave becomes weaker and weaker as the particle gets closer and closer to the horizon. And the decay rate is controlled by how fast this particle gets to the horizon. To give you an example, here we can look at numerical relativity waveform. This gray curve is the numerical relativity 2-2 harmonic from numerical relativity simulated for a GW1509-14-like system. Apparently, you can see quite clean late in-spiral merger and rain down stage. Using a method to remove those quasi-normal modes, we obtain this black curve. And you can see that there are a few oscillations over here, which look like a mode, but they don't belong to any quasi-normal modes. And it turns out that those few cycles are sourced in the neighborhood of horizon. Why is that the case? Because in our previous paper, we use a theory to develop an analytic model, which is shown as this black curve, black dashed curve, and the agreement is fairly well. So this gives us some sort of confidence that those cycles are sourced in the neighborhood of horizon. And currently, I'm able to develop some solid theoretical method to put this phenomenon on a very solid background, at least for memory in structured spacetime. After reviewing this signature from numerical relativity, it is also interesting to see whether we can observe this part from real observational data. So on January 14th, 2025, the LIGO-Virgo-Kagura collaboration observed is the largest gravitational wave event to date. This noisy gray curve is the raw data after whitening. Because this event is so loud, we can actually see the gravitational cycles, especially the late rain-down stage. And by the way, this red curve is the best fit from numerical relativity waveforms. Then we use some data analysis pipelines that we developed to subtract quasi-normal modes, and we obtain this middle panel. You can see that those quasi-normal mode cycles, those quasi-normal mode cycles are basically gone. You see, in original signal, there are some quasi-normal mode cycles, but then in the middle panel, those cycles are basically gone, and we are left with this heartbeat-shaped pulse. The late part is emitted from this near horizon region, and using our analytic tool, we can do a Bayesian analysis, and we can further subtract this component from the middle panel, and this gives us to this bottom panel. So again, in this case, those cycles are gone. So this suggests that the data are consistent with our theoretical interpretation. We can also extract the frequency and the decay rate from those few cycles. Those contours are the 90% credible region that we extracted from that time window, from that wave component with different starting time. Here, our start time range from -9 all the way up to -3. At the beginning, you can see that the posteriors still evolve a little bit. This is because the particle still undergoes dynamical evolution in the neighborhood of black hole horizon. But they all cluster around this red region, which is so-called horizon mode. For this horizon mode, its frequency is around 2 omega h, where omega h is the horizon rotation frequency, and the decay rate is the horizon surface gravity kappa. So here, by analyzing this event, we can really use real observational data to touch the near horizon region. It is quite cool, isn't it? So here I don't have more time to jump into technical details. So feel free to wait for our paper, which will appear in Nature very soon. So actually, this is my last slide. So to summarize, in this talk, I covered a few nonlinear phenomena, including mode nonlinearity and also dynamical nonlinearity. I also mentioned Cauchy characteristic matching, and using this method, we can review tail from merging binary black holes in the fully nonlinear region. And finally, we are able to identify this near horizon source-driven emission, not only in numerical relativity waveform, but also in real observational data. Right now, our theoretical development for this source-driven emission is still ongoing, and I would like to highlight that right now we are developing some AI agent to basically completely handle all the theoretical calculations related to black hole perturbation theory. And with that, let me stop here and take any questions.
When you were talking about nonlinearities and this wave injection, did you look at resonances? Because you had mentioned that a cubic order, you could get a resonance with it.
Oh, I see. Yes, I think I remember that. Well, I hope you like the comments.
There's no rush.
I have a military training. In the So it shows you 10.
Yeah, I won't be long. But yes.
Okay, we're gonna get resume the last talk from the morning session. Our speaker is Lawrence Werner from Nottingham. We'll read more about black holes.
Yes. Thank you, Luis, and thank you to the organizers for inviting me. I'm going to continue along similar lines from where Zheng left off, talking about linear black hole perturbations. And in particular, I want to explore more the question of how black hole quasi-normal modes get dynamically excited. And I want to put this in the context of gravitational wave astronomy. Typically, we say that quasi-normal modes describe the ring down, so the final stage of a binary black hole merger at intermediate times. In gravitational wave astronomy, this means that at those times, the waveform is described by a superposition of these damped sinusoids, these complex exponentials with some amplitudes and phases. And these amplitudes currently in waveform models and in data analysis are taken to be constants. And they're obtained in various ways by fitting numerical relativity simulations. They can also be left unspecified and determined directly from observations. Or they can be modeled in some cases, assuming that the secondary black hole is very small, is just a point source plunging into the primary black hole. There are, of course, clear limitations to this because in the full waveform, we want to connect the ring down to the previous stages of binary evolution. And these quasi-normal modes need to be excited at some time to turn on in some way. So again, in current waveform models, there are some ad hoc turn-on functions, activation functions, to be able to connect these stages. But of course, we would like to do better. As Zheng mentioned, we think there are nonlinearities excited in the ring down, and we can imagine that they would be most excited exactly in that same region when linear quasi-normal modes are also excited. Also, higher quasi-normal modes with higher overtone number decay rapidly, right? So they are most observable right at the beginning of the ring down. So, and of course, the signal is also largest in that region, right? So there's many reasons why we want to understand the dynamical excitation better. So in this talk, I'm going to take two different approaches. First, I'm going to look at quasi-normal modes as mode solutions, so in frequency space, but I'm going to try to move towards the dynamical picture by using different coordinates rather than the standard Boyer-Lindquist coordinates, and using hyperboloids. And in the second part of the talk, instead, I will abandon partly this mode picture and use some time domain methods. So let's start with the first part. This was work with Marika Minucci, a postdoc at I think the Niels Bohr Institute right now, with Panosso Macedo and Cristiana Pantelido. So to understand, one important feature of quasi-normal modes, which you've heard about in Steven's talk yesterday, is that they are orthogonal under a suitable bilinear form. And this is to remind you what the bilinear form looks like. It's composed of a conserved current, the symplectic current of the Tchaikovsky equation, and the insertion of a symmetry operator of Kerr, the T-phi reflection, which is playing a double role here. It's ensuring orthogonality, and it's also mapping S to minus S solutions. But one challenge with the bilinear form was when we were using the standard Boyer-Lindquist coordinates, was that our quasi-normal modes were actually divergent at the two boundaries of these slices, at the bifurcation surface and at spatial infinity. And in Steven's talk, you heard that many people have proposed ways of regularizing quasi-normal modes in these products. For example, you can use a complex contour which goes around this branch cut of the mode functions that originates at the horizon. So going around this problem is one reason, on top of trying to move towards dynamics, to try and use different coordinates. So here come, therefore, the hyperboloidal foliations, which are essentially, these slices that connect to the more interesting boundaries of our space-time, the future horizon and future null infinity in this case. They are built quite simply with a coordinate transformation that mixes the time and spatial original coordinates. And to simplify the quasi-normal mode problem further, you can also do a spatial compactification and a conformal rescaling to absorb some of the spatial scaling of the mode functions. These are the future hyperboloids, but you can also build past hyperboloids that connect the past horizon and past null infinity. And the difference is just a sign over there. And here I'm going to use as the height function, this function that is, producing your hyperboloids, this form here, the minimal gauge, known as the minimal gauge. So the power of these hyperboloids is that not only they connect to these nice regions of the space-time, but they also regularize the QNM solutions. So in particular, QNM solutions that are regular on future hyperboloids are the retarded QNM solutions. So they are outgoing at those future boundaries, while QNM solutions that are regular on the past hyperboloids are instead outgoing at these other boundaries down here. Okay, so that's very nice. And so based on this, you could have hoped that the bilinear form would now be regular on the hyperboloids. Unfortunately, this is not the case. And this is because that T-phi reflection that we have to insert in the bilinear form in order to obtain orthogonality is actually mixing retarded and advanced solutions. So it's mapping one into the other, or mapping future hyperboloids and past hyperboloids. So that means that if I want to look at the orthogonality between two retarded quasi-normal modes, one of them is going to be mapped into the advanced solution and is going to be irregular on the hyperboloid that I've chosen. By the way, I know that I'm the third talk of this morning, so I've sprinkled some cats throughout my slides. If you get bored, you can count them. Okay, so because the bilinear form is still, divergent, not well defined on hyperboloids, we realized that we still needed to resort to regularization. But this was quite simple because we could just, do a coordinate transform to the contour we were using in the coordinate R to this new contour in the hyperboloidal coordinate sigma. And, it takes a funny shape, but it performs the same task. And so once you define the bilinear form on that contour, you can find that it's finite and independent of the slice you take. Okay. But going back to the dynamics, so far, the way to establish how quasi-normal modes are excited is to compute their excitation coefficients. And in Stevens' talk, you saw how these were connected to the bilinear form, and we find exactly the same in the case of hyperboloidal slices. So if you have some initial data on your first hyperboloid, you can project it and normalize it using the bilinear form to find these excitation coefficients for the quasi-normal modes at late times. And you can check this explicitly comparing term by term the expression on the right with what you would obtain with the Green's function. However, the excitation coefficients themselves cannot be the whole story when we talk about the dynamics of quasi-normal modes, because again, these are just constants. And for example, they're not accounting for any causality, for the fact that it will take some time for all the initial data to come into causal contact with our observer. They also don't take into account the fact that we might have time-dependent sources like the particle that will eventually generate the ring down on the right-hand side of the Tchaikovsky equation. And they also don't account for quasi-normal mode incompleteness, which I left very unspecified with those dots on the right-hand side. So this motivates trying to use different techniques, or kind of going back to the drawing board and look again at how we derived the expression for the excitation coefficients and what we left out in that process. So this was work led by Marina De Amicis, who's a postdoc at Perimeter, and also with Enrico Cannizzaro, Gregorio Carullo, and Adrian Kunz. So the setup to understand this dynamical excitation of quasi-normal modes again will be to stick to linear perturbations of a Schwarzschild background and incorporate now the source of a smaller black hole that will be in spiraling and plunging into the main black hole. And this might seem like strong assumption, a bad approximation to the gravitational wave systems we currently detect, which are more comparable masses. But there's been a lot of work in the past 20 years in the small mass ratio expansion, as it is called. And you can see that if you compare numerical relativity simulations with these small mass ratio waveforms in Schwarzschild, and if you look at the right comparison, so numerical relativity simulation with a large mass ratio, 1 to 15, and a non-spinning remnant, so that it's consistent with Schwarzschild, you actually find a very good agreement. So this will be our motivation to choose this setup, which is, of course, simpler than the comparable mass case. Okay, so we said we want to go back to the drawing board. So let's look at gravitational perturbations in Schwarzschild sourced by our point particle. So this will mean that we want to solve the Reggie-Wheeler or Zerilli equation with a source. And a beautiful tool to do this is the Green's function. So in the time domain Green's function is what we want to eventually use. But the first step will be to build the frequency domain Green's function. So if we place our observer further away than the source, so R star our observer and R star prime our source, then the frequency domain Green's function can be built from this combination of independent mode solutions of the Reggie-Wheeler equation. And we choose for kind of the observer side, the outgoing solution at null infinity, and for the source side, the ingoing solution at the horizon. And W is just the Wronskian between the two solutions. We know quite well what the analytic structure of this Green's function is. It has poles at the quasi-normal mode frequencies that come from zeros of the Wronskian, and it has a branch point at omega equal to 0, which comes instead from the structure of the mode functions themselves. And so the standard law to construct now the time domain Green's function is to Laplace transform back to time. So this would have been an integral over the real line just above the branch point. But to make it more explicit that we have quasi-normal modes in our problem, we will usually say we close the contour in the lower half plane and pick up the residues at the poles and some branch cut and some arc contribution. And so naively, this is what we would call the quasi-normal mode Green's function, right? The part only coming from the residues. However, this idea that we would always close the contour in the lower half plane is not quite right or quite useful, because really we want to do that only when the integral over the arc is 0 or at the very least finite, right? Rather than expressing our original integral into a sum of divergent contributions. So we want to find the condition to be able to close the contour in the lower half plane. In our work, we actually restrict ourselves to a simpler condition, which is just the requirement that the QNM sum at least converges as we sum over an infinite number of poles. And this is what the QNM sum for the Green's function looks like. There are some excitation factors that are essentially the derivative of the Wronskian or the norm of the mode. And we have what are essentially the series part of Lever's solution for the quasi-normal modes. And then this is instead the exponential part of Lever's solution. Okay, so some parts of the series are well understood analytically. For example, the behavior at large n of the excitation factors is known, and also of the frequency. But Lever series is a bit more complicated, especially if we want to, determine a convergence condition at all values of the Green's function argument. So we don't want to use any asymptotic expansions at large R star prime or R star prime going to the horizon. We want a general condition. So we resorted to exploring this numerically, and we found that the condition is the one I wrote over there. So this condition is essentially a scattering condition. It means that if our source R star prime is at positive R star, so to the right of this so-called bounce radius, R star equals 0, then the observer far away, our new cat, will receive quasi-normal mode signals once the signal has had time to scatter off the bounce radius. Instead, if the source is located to the left of the bounce radius, QNMs can propagate directly inside the light cone. And I also depicted this here. So again, to the right, we have scattering, which is more restrictive than the light cone. And to the left, instead, we have the light cone condition.
Do you guys understand why that is not a free?
Yes, so I was trying to mention here that this bounce radius is not the light ring, and it's not the peak of the potential of the Reggie Wheeler or Zerilli potential, which is quite strange. There's been just last week or 2 weeks ago a paper by Ben Withers and his PhD student Carvalho, where they found that this bounce radius is related to some complex geodesics that bounce at the singularity, and which seem to be related to the convergence radius of the quasi-normal mode sum. But yeah, that's all I can say. Confusion, yeah, I don't know. Yeah. Okay, I wanted to stress that this QNM propagation condition is not the same as causality, and therefore there will be different parts of the Green's function that are propagating with a delay with respect to each other, right? So if our source R star prime is still to the right of this potential barrier or bounce radius, we can actually split the Green's function into two pieces. One that still has the quasi-normal modes, the poles, and one that only has the branch point and branch cut. And you can split the space-time in different regions, and in these different regions you find different convergence conditions, and therefore you need to close the contour in different ways. So what we were talking about previously was this QNM region, where you can actually close the contour for both pieces of the Green's function in the lower plane. But there is a region between the scattering condition and the light cone where you actually need to close this part of the Green's function in the upper half plane, and therefore you lose the QNMs. So this is what people have referred in the past to as the prompt response. And finally, of course, there's a region prohibited by causality where you close both Green's functions in the upper half plane and you get 0. Okay, but we want to forget, for now at least, about the branch cut and other parts of the Green's function and only focus on quasi-normal modes. And so the more appropriate definition of the quasi-normal mode Green's function needs to incorporate this propagation condition or convergence condition. And so we will have it there as a Heaviside function. Okay, so we dealt with the first piece of the puzzle. The second piece is the point particle source, which I've written down here a bit more explicitly. So this will oscillate with the orbital frequency of the particle and is localized on the particle trajectory, for which we will choose a circular in spiral that transitions to a plunge. You'll see in a moment that it's important that the point particle source has two kinds of pieces, a delta function and a derivative of the delta function. And this is important because we will convolve the source with the Green's function, right? So we will have two integrals. And the delta function can get rid of one integral, but not both. While with the derivative of the delta function, we can get rid, by integrating by parts, of both integrations. Okay, so finally we can put all these pieces together and come up with an extended definition of the excitation coefficients that takes into account this Q and M propagation and also the presence of the source. So this is what I've written over there. And I've divided it into, according to these two pieces of the source, into two types of excitations. One is this activation type excitation, which still contains an integral and therefore accumulates over the trajectory of the particle up to the apparent location of the particle as seen by the observer. And instead, the second coefficient is more of an instantaneous excitation that depends only on the apparent location of the particle and doesn't accumulate over the evolution. And of course, the apparent location needs to be determined with the right propagation condition, depending on whether you're to the right or to the left of the bounce radius. Okay, so let's finish off by looking at all this in terms of some nice plots. So the first one is kind of the main punchline. This is the full quasi-normal mode signal generated by the plunging particle. I'm adding up an increasing number of overtones of quasi-normal modes, and I'm showing kind of the largest number in pink. So that's the closest to the full quasi-normal mode signal.
Excuse me, for L equal 2?
Yeah, L equal 2. And the dashed line is instead a full numerical solution of that sourced Reggie-Wheeler or Zerilli equation, which therefore contains other parts of the signal, other parts of the Green's function, right? The branch cut, the front piece. So we see that from when the particle crosses the bounce radius, the Q&M signal actually completely reproduces the full signal, right? Which is very nice. But instead, of course, at earlier times, the front piece, the direct emission of the inspiraling particle is still very important. And therefore, the quasi-normal mode signal doesn't match at all. So to unpack this quasi-normal mode signal and actually kind of answer the original question of this talk, we can also look at these excitation coefficients as a function of time. So in the standard picture, we would have said that the amplitudes of the quasi-normal modes are constants. And instead, in this better model, we find that they evolve over time, right? They kind of peak around the crossing of the bounce radius, and then they settle onto a constant only at late times. And I think it's important to note that even after the quasi-normal mode signal has become the dominant part of the signal, a good description of the signal, the amplitude is still not constant, not quite constant. here I'm showing both these kind of accumulation type coefficients and these instantaneous coefficients, and they have exactly the behavior you would expect. One accumulates and the other one instead peaks around the bounce radius and then decays. And all this was for the fundamental mode. But if you look at the overtones, the picture actually is a bit different. I'll give you a second. What you can see is that these overtones, for the first overtone, you cannot see it quite clearly. It seems to settle to a constant, but not quite, you cannot quite tell. But for the second overtone already, you can clearly see that it's growing at late times, its amplitude. Luckily, this is just an artifact of looking in a sense at the wrong quantity, because the actual physical observable is not the coefficient there, C or I, but rather the full waveform, which also contains, of course, the exponential decay of the quasi-normal modes. So if you look at actually the waveform of each pole, coming from each pole, you see that it does decay at late times. So everything is good. However, if you stare a bit more closely at this picture, you realize that everything is fine, but maybe not quite what you would have expected. Because you see that the fundamental mode in green is decaying at a different rate from all the other modes at late times, right? And all the other modes instead are decaying all at the same rate, which is not what you would have expected because they all have different imaginary parts to their frequency. They seem to decay at the right rate at intermediate times, but not at late times. So what's going on? Not a cat. What's going on is that what you see at late times and what Xinjiang was also finding is the role of the source. Because as you approach the horizon, the quasi-normal modes are contributing with their own personalized decays. But you're also convolving with the source, which is instead, approaching a universal horizon behavior. It's decaying a leading order with the horizon redshift. And the horizon redshift numerically is such that the source decays faster than the fundamental mode, but slower than the overtones. And therefore, at late times, you see the fundamental mode decay, but for the overtones, you see the source taking over, and therefore this redshift component. I should say that there's been some controversy in the literature. Some previous works had found that actually the leading redshift component has 0 amplitude, while we don't find this. So yeah, maybe, I'm not sure why. It could be that other parts of the Green's function cancel this leading order redshift component, but I'm not quite sure. Okay. And the last thing I want to mention is that it's nice to also understand a bit more the physical mechanism of quasi-normal mode excitation. And we can understand this by looking at both the frequency of the signal, the total signal, frequency of the total signal, and also by looking at the relative phases of different modes. So what you see at early times is that the frequency is being driven by the frequency of the particle, which is this dot-dashed orange line. And the phases are approaching pi. So the modes are being excited in counter phase. And so this matches this kind of forced harmonic oscillator picture, right? The quasi-normal modes are actually kind of collectively getting excited and forced by the particle. And even though their amplitudes would be quite large, taken singularly, they are in counterphase and they are destructively interfering in this excitation. Instead, at late times, as the source has decayed, you see kind of a free oscillator, right? The frequency is approaching the frequency of the fundamental mode, and the modes are actually now in phase. There's some more dynamical transition going on at intermediate times, but at least in these two regimes, this is what we find. Okay, so this brings me towards the end. To summarize, we think by putting together actually very simple ingredients, the quasi-normal mode Green's function and the source of a point particle, that we've gained some better physical understanding of the dynamical excitation of quasi-normal modes. We've seen how the amplitudes behave over time, how they grow over time. We've seen the emergence of the source, the redshifted source at late times. And we've seen this transition from driven to free excitation. So now if you've counted all the cats correctly, I have a small treat. Stephen and I are based in Nottingham, where actually Giorgi Green was born and raised. And if you ever come to Nottingham, it's really nice to visit the Green windmill, which was owned by the Green family. So Giorgi Green worked at the family mill and was completely self-taught, which is amazing. Yeah, apparently he was working on Green's functions when there was no wind, so when he could take a break from the mill. He made all these amazing, developments in mathematics and in physics because he was self-taught and therefore was not forced to use Newton's methods for calculus like everyone else in England at the time, and could instead choose to use Leibniz's calculus. And final part of the story, he, even though he was self-taught, he really wanted to go to Cambridge or Oxford, but at the time you had to be a bachelor to attend. And therefore, even though he had several children with a woman in Nottingham, they never married, so that he could eventually go to Cambridge. And that's all.
So besides, what does Stephen do when there is no wind? Questions for the ready.
I'm ready, yeah.
Okay. Hello again, everyone. So for the first talk of this afternoon session, we're happy to have Dietrich Hefner from Université Grenoble-Alpes, who's going to tell us about linear perturbations of Kerr black holes, classical and quantum aspects.
Okay. Thank you. So I first would like to thank the organizers for organizing this conference. I think we had so far a very great conference. Personally, I've learned a lot during the talks. And of course, also for giving me the opportunity to speak here. So I will speak about linear perturbations of Kerr black holes, a little bit what we can show. And I will speak as well as on classical and quantum aspects. The quantum theory on Kerr black holes is quite interesting. So which will be more towards the end. I hope I have some time to explain this in detail. So this is some kind of overview talk based on joint work with different co-authors. So the principal part, I think, is with Peter Hinz and Anders Schwasi. So this is on linear stability for the Kerr black hole. And one aspect of this is the mode analysis, which I have done with Lars Andersson and Bernard Whiting. And the quantum part is with Christiane Klein. So we are interested in the Einstein vacuum equation, and my signature will be plus minus minus minus, which is for manifold. So of course we all know this solutions. So Minkowski space and the Schwarzschild metric. So this, of course, you all know and have been introduced by Michalis too. So the important point is that this is a 1/r perturbation of Minkowski space. So this will be important later on. So, so this is explaining essentially the coordinates. So this T star is a null coordinate close to the horizon and close to so this will be okay, and close to null infinity, and then there will be also this frac T coordinate, which looks a little bit like T star close to the horizon, but then rather than Boyer-Lindquist at infinity, right? And so we are going a little bit beyond the event horizon, so this is with sigma fine. Okay, so this is a picture. And now let's go to Kerr. So all I will say will be for the whole sub-extremal range. So there's no restriction on A, whatever result. So you see, so what are, I just want to explain what are the important informations for us. So first of all, this is a 1/r2 perturbation of Schwarzschild. And so the second point we have already seen, so this is with coefficients in front of a dt squared, which changes sign outside of your event horizon. And this makes that dt is not globally time-like in the outside region, but of course the problem is deeper than that. There is no time-like Keeling vector field outside the event horizon. Okay, of course we lose spherical symmetry, but Kerr still has a lot of symmetries. I mean, this is very interesting. And one thing which is quite interesting are these principal null geodesics, principal null directions, which are very important for the construction of Kerr. So let me briefly recall what it is. So take a point on your manifold, and then if you have g of v and v plus minus x equals to 0, so this implies that the Weyl tensor evaluated at v plus minus v, v plus minus and w is 0 for all w in the tangent bundle. So this is some kind of double roots of the Weyl tensor. So we want to analyze hyperbolic equations on this kind of space-time. So what do we really need to understand? So first of all, what is very important is that Kerr is asymptotically Minkowskian. This will tell us how is the low frequency behavior of these waves. And then another point which is important is this trapping, that I like to look at the cotangent bundle. So, and this gives you a picture that you all know from teaching ODEs, right? So this is hyperbolic trapping. So what is happening here is that you have a trap set K, and then you have stable and unstable directions. And so you have some expansion rate transversal to K along, for example, this unstable direction, and also in the other time directional rate on the stable manifold. So this is how it looks like. You know, this is hyperbolic trapping. In Kerr, something more interesting is happening. So now, of course, I mean, K has its own dynamics in K, and this can have expansion rates too, but these expansion rates are very small with respect to the expansion rates that you have in the transverse directions. And this smallness is measured by this R. And what is happening in black hole spacetimes is that this is R normal hyperbolic for all R. And this is a stable property. So you check it for one Kerr, you perturb it, the trapping remains the same. And then this is very interesting for perturbing black holes. So I already said there doesn't exist any global timeline Keeling vector field outside the black hole. And the consequence is there is a priori no natural conserved positive quantity I could work with. So we have the analog with positive cosmological constant, this is with this Kerr metric, and the picture remains the same, but the asymptotic behavior is different. And this gives a completely different low frequency behavior and a much better decay. And this is just because of the low frequencies. All this trapping stuff and so on is the same. So the initial problem, we have seen this before, so I think I can be very quickly on it. What you will give yourself is a Riemannian manifold with some symmetric two tensor, and we are looking for Lorentzian manifold M. So sigma should be a slice of it, which is flat. And if you take, now I have to take a minus, so if you take minus G restricted to sigma, then this is your Riemannian metric, and the K is the second fundamental form of sigma in M. And now with the necessary and sufficient condition to solve this locally are the constraint equations, and then you can do it. This is the famous theorem by Giorgi. And if you take Kerr initial data, you get Kerr. Of course, there are some issues of uniqueness, but in principle, this is uniqueness, of course, up to diffeomorphism invariance. And the stability problem is the following. So take data which are very close to this data, and then what you expect is that somehow your metric will converge to another member of a family. So with some kind of orbit stability. It's not stability of a single member, it's the orbit stability. And you expect in Kerr that this goes in an inverse polynomial weight. So there has been a lot of progress on that. So the first result for stability is the stability of a Kerr-de Sitter family for very small angular momentum. And the convergence is exponential. And this has to do with this asymptotic behavior. So this is by Hinz and Basi. By Hinz, we have stability of a Kerr-Newman de Sitter family. And there's also a result which is conditionally for large A. So what they have to suppose is mode stability. I will come back to this later on, but the whole, say, framework works perfectly fine for large A. So this the only point is mode stability. Then there's the stability of a Schwarzschild family by Dafamos, Holzhege, Rodniansky, and Taylor in 21, and the works of Kleinerman, Scheftel, Giorgi, Kleinerman, Scheftel, and Chen about the stability of Kerr for small a. Okay, so this is enormous progress. I mean, there have been so many people working on it with so many new ideas. So this is enormous progress. So what one can say is that, so one thing is that many of this is restricted to small a, whereas the physical relevant case seems to be large A. And so some of this works are a little bit long, so I can perhaps rethink about it a little bit. Okay. So I will only speak about linear stability, but nevertheless, one should keep in mind the nonlinear problem. And some issues one has to keep in mind. Of course, one has to find this final black hole parameters. This is one issue. We have, as Michal has already explained in his lectures, we have this diffeomorphism invariance. And this means that there's no prescribed type. So at some point, you have to fix a gauge. And somehow once your gauge is chosen, you have to somehow be able to localize your black hole in this fixed gauge. And of course, in contrast to the de Sitter case, we will have quite weak decay. So you really have to understand the nonlinearity in detail in contrast to what happened in the de Sitter Kerr case. But then, very naively, you can hope that some iteration scheme that each step you solve a linear equation may work. But of course, for the linear equation, it won't decay to zero, right? I mean, they're linearized curve, there are all sort of gauge solutions and so on. So you really need to to read of an improved case of a final black hole parameters, the location of a black hole velocity, and all this kind of stuff. So this you have to keep in mind. I mean, if you want to formulate a linear stability problem. Okay, this is very brief introduction. Are there any questions on that? Okay, everything is fine. So let me come to the linearized equation. So this is first formulation of a result. There will be essentially two formulations, one without gauge fixing and one with gauge fixing. So this is with fact t variable. So you remember this is now close to Horizon, and when this is like Breuer-Lindquist, and it's Breuer-Lindquist at infinity. Yeah, so we give data which decay like R to, so sorry for that, I'm really not, okay. Which decays like R to the -1 minus alpha, respectively R to the -2 minus alpha. And then you need similar estimates for some derivatives. Here are 8. Okay, I can look there. Okay, and then let H be a solution of linearized Einstein equations with this data. And then what the theorem says that there are linearized black hole parameters and the vector field such that the solution is a linearized Kerr plus a Lie derivative of Kerr with respect to this vector field. So this is a pure gauge solution, plus something which is decaying and which is decaying like t to the -1 minus alpha plus some small error. So here linearization is really to understand in a very naive way. You take G the B plus SB dot and take the derivative at S equals 0. So this is a naive way of thinking about this linearized curve. So this is the result. And so there are several aspects of that. So I will speak a little bit about gauge fixing, because of course, first of all, to show it, you will have to fix a gauge. And then I will argue that even it is interesting to formulate a result with a gauge fixing, because this gauge fixing will clarify which somehow poor gauge solutions you will permit. Okay. Okay, so we will use generalized harmonic gauge. So this is the way I think about it. So there's the one form called W of G. And the vanishing of this one form characterizes that the identity is a wave map between your manifold equipped with your metric G and your manifold equipped with your metric GB. Okay? So this G is a usual twice reversal operator in 4 space-time dimensions. And then you add these gauge conditions, meaning that you don't look only at which G equals 0, but also at W of G equals 0, and you put some initial data. And the claim is that this is equivalent to an initial value problem for this one. So one direction is obvious, and for the other direction, you use second Bianchi identities, and this will give that your gauge 1 form fulfills a wave equation for 1 forms, and the initial data is 0. To take some kind of first derivative, you need constraint equations, but the data is 0. The 0 data propagates because it's a hyperbolic equation. So this is propagated. So this is really equivalent. And you can play the same play on the linear level. So this is the linearized version of it. Okay? So this is the starting point. So this is the usual harmonic gauge. And we will see what is going on with this gauge. So this is my operator, and there are some issues about it, as you can imagine. So the first issue that you have some mode solutions, and this come from Coulomb type solutions of a one-form wave operator. Okay, where does this come from? If you take the usual one-form wave operator, say, and omega is the solution, when d omega is the Maxwell field. And Maxwell field just in this kind of geometry has Coulomb solutions. So this is very natural, this comes in. And the second point is, if you do it like that, you can't put linearized Kerr in this gauge. Because if you write down your equation, because this has a kernel, you can see, this is computing some pairings, you can see that this you can't solve away. So you can't put it in your gauge. If you keep it in this gauge, it will show up at the level of going solution, but this is something you don't want, okay? This is the first issue. And more generally, you will find generalized mode solutions, which are quadratically going in time. Okay, this is something you don't want, so I will argue a little bit later. So if you fix your gauge, ideally, what do you want? You want to permit translations at infinity, rotations, and boosts. So you have to permit mode solutions which are linear going, but not more. So with quadratically going mode solutions are not good. So what can we do? So what we have to understand is that in this kind of gauge, there's a lot of flexibility. Okay, we can write it like that, but we can do something else. So we have essentially two possibilities. So I should perhaps say, so this is, so in my notation, so this is the divergence operator, and this is symmetric gradient, right? Okay, so you have two possibilities. You can change the gauge. And this is changing the divergence operator. So what does do a divergence operator? It takes the symmetric 2 tensor, it makes a 1 form. So we add something here with a small constant, but just the same thing, okay? So this is we change the gauge. So there's some flexibility. So this C epsilon is a compactly supported 1 form. So the compact support is important because, as I argued at the beginning, the asymptotic behavior of this spacetime is very important. And this, of course, is translated in the behavior of my operator. And this asymptotic operator, I really don't want to change. So concretely what you do, you start with a usual wave map gauge, and then you change. But you don't want to redo your analysis. Okay, so compactly supported. The second thing that you can do is you can do constraint damping. This is somehow you change the implementation of your gauge. Okay, if you look at the implementation here, so this symmetric gradient also I can change. Okay. So, and also, I mean, you sit down and write down what is coming up in your mind. Something, take a 1 form, make out of it a symmetric 2 tensor. Okay, these are the two things that we use. So this constraint damping is known. We learned this from numerical analysis. So numerics people know this very well. I mean, if you don't choose correctly your gauge for numerical analysis, when everything's blowing up and you can't understand anything. So this is very known in numerical analysis. So I've written some names here: Brodbeck, Frittile, Huebner, Euler, Gundlach, Calabrese, Hinter, Martin, Garcia. Okay. And so in addition to your linearized Einstein operator, we have at the permanent level 2 operators on 1 forms that you have to control. One is what we call the gauge potential operator. So if this operator hitting on the 1 form is 0, then the symmetric gradient of the 1 form satisfies the linearized gauge condition. And the other operator is the constraint propagation operator. So if you have solution of your linearized Einstein equation, then this 1 form satisfies this equation. Okay, these are 2 operators that you have to control at a permanent level. And in particular, the mode analysis has to be done for all Fourier operators. Okay, any questions on that? So let me give you the result now. So this is now a gauge fixed version. And it says, so essentially, to get rid of these solutions we don't want, these are essential perturbation arguments. So the constants are small, the C's are compactly supported, and again, I take initial data which is decaying. But this time I have a perfect hyperbolic operator. I don't mind about constraint equations or whatever. This is a perfect hyperbolic operator, which has some initial data which is decaying like that. And when the solution writes in the following way, a linearized curve, but this is now put in the gauge. So the claim is that I can arrange with constants, with C's, such that even the linearized, with respect to the mass, I can put in the gauge. So this is the gauge fixed version of this. When you have two types of gauge fixed solutions, the first one, with a lever derivative with V1, so this is exactly what I said, what you have to allow and what you expect. So some translations in space, some rotation. So this V1 is in a fixed six-dimensional space. Then you have something which is decaying. And then unfortunately, but this shows up, you have a gauge solution which itself decays, but on a lower level. But this we at some point we thought it doesn't show up, but this really shows up. So this you have to keep in mind. Okay, let me comment on this. So this is somehow, if this was not there, then it's somehow what we really wanted to show. This is there, and it sits there. So let me discuss this. Or at least are there any questions on this theorem? No, okay. So you can read of the change of the black hole parameters because of this linearized curve solutions. You can follow the movement of the black hole in the chosen gauge. And then, so one way to get rid of it is the following. So you look at the version where you impose again the constraint equations and you fix the gauge. But it's not a gauge equals to 0, but you permit the gauge source term, which is linked to this solution which appears. And then you can get the decay that you want with -1 minus alpha. Okay, so there's prior work on that. So I cited what is closest to us perhaps. So this work, first work was, I think, by the pharmaceutical Giorgi, who do this for the Schwarzschild case. And then there's work by Anderson, Bechdel, Blue, and Ma. In 19, so there's faster decay on the initial data. So this kicks out the linearized curve as far as I understand. And there's also, so this is for slowly rotating, but there's a conditional result for the whole sub-extreme case. So if you have a more that's estimated a priori, then you get this automatically, okay? So this is what it is. And then there's a result for weakly charged and slowly rotating by Lily He for the Kerr-Newman spacetime. Okay, so this is what it is. So are there any questions on that? If not, I will just, so I can't really go into details, but I try to explain the global strategy of the proof and what is, from my point of view, important. Okay, let me do this. So we work on the spectral side. And what you see here, so if you have this kind of formula, and then you see, so this is something which is their basic principle in Fourier analysis. So decay on the physical side corresponds to regularity on the Fourier side. So imagine what I can't do for the moment. Imagine that I can go down to imaginary part equals to 0. And then I multiply this with a T star. So the multiplication by T star is derivative with respect to sigma of this one. And then if I have enough regularity, I can do integration by parts. So this translates decay in physical space to regularity in Fourier space. So, going down to imaginary part of sigma equals 0 is quite a story. So you start with imaginary part of sigma very large, and this essentially you get by the first energy estimates you write down. Essentially, you need some exponential control of your solution to do this. And then one very important point I really want to insist on. So from our point of view, the important thing is to have a Fredholm setting. I will give one example. You have this result by Bernard Whiting saying that you don't have mode solutions. Does this give control on your solution a priori or not? You know that you don't have somehow point spectrum in the upper half plane, but all kinds of horrid stuff can happen nevertheless. So the idea is, can this be an analytic family of Fredholm operators in sigma? And at this point, you know that your problems somehow are isolated. So this is really the starting point. So can I get in this setting a Fredholm setting? And if you have a Fredholm setting, then excluding, so this is growing, is just the question of modes. So this starts, of course, with a Whiting result for Tucholsky, and then you have to go to the linearized Einstein equation, to the one-form operator, and so on. But morally, this goes down to Tucholsky. So I've already spoken about the change of gauge and the constraint damping, and now it's completely separated. You have one high frequency problem and you have one low frequency problem, and this is now completely separated. So you don't have to get any headache how to fix this up. It's quite from the beginning, it's separated. Okay? So the mode analysis, this I have done with Lars Andersson and Bernard Whiting. And this uses, of course, the initial result of Whiting and some result by Andersson, Ma, Pagadini, and Whiting. And we also, so I don't have to speak, I have time to speak about it, but we use this classification of gauge invariance for linear perturbations of Kerr by Andersson and different co-authors. And then, so this is some of the initial gauge. And then the constraint damping was in principle already done in our original paper for small a, and was done by Peter Hinz for large a in another paper, this gluing paper, where you lose a black hole to a time like geodesic. So say the important point is really this Fredholm setting, and I want to try to explain this a little bit. These are the estimates. So there are a lot of indices. I try to explain this. This is the estimates we get. And I will try to argue why these are the good estimates. So I wanted to write entire the theorem, but don't look too much at these restrictions. I just want to explain the philosophy. So you have the Sobolev spaces. So the bar is just that it is based on extendable distributions, which have two indices. S is measuring regularity, and L is measuring decay. Okay, and B is for B Sobolev spaces. So Elena spoke a little bit about this morning. So this is based on the thing that you use vector fields which are tangent to the boundary that you look at. Okay? So what is important here is that these indices are smaller with A naught and with A naught. Okay? Meaning that the corresponding Sobolev embedding of this one in this one is compact, right? And this gives you a Fredholm setting just because on the kernel of this one here, now the norms are becoming equivalent. So your unit ball is relatively compact and then finite dimensional. Okay, you need you need corresponding estimates for the adjoint operator, right? To get the co-kernel. Okay, but this is the principle. Okay, so there are different estimates that you need. You need this as low frequencies, which will have to do with your asymptotic behavior. You need this at intermediate frequencies, and you need this as very high frequencies where it turns out that this last term you even don't have. Okay? So let me try to convince you why this kind of stuff could be true. Okay. So I don't know, we have seen this week this talk about propagation of singularities. So if you have a propagation of singularities, it's a little bit different. What does it give? It gives you this kind of control, but for you, localized somewhere micro-locally. If you have this kind of control for you somewhere else, and both are related by the Hamiltonian flow. Okay? So this is, so this is usual propagation of singularities, and y isn't the right term here. So if I have it, I don't have a four-term estimate, so it doesn't help. So let me explain. So this is written here down, that's that these are four-term operator of index 0. This is a picture of Hamiltonian flow in a Kerr spacetime. So these are points above the horizon with A minus, A plus. And these are radial points. You don't have propagation on the base manifold from a Hamiltonian flow, but you have some dilation in the fiber. And somehow the regularity, if you go in the good direction, is going there. And this gives you, this is very similar to the redshift effect. It's another point of view, but this is the stabilization effect at the horizon. And this gives you some a priori regularity. And this so somehow your procedure, you have to initiate somewhere. And once you have it, you propagate it around. Of course, there are complications. This is the trap set that you have to understand. But essentially, you initiated something. Interestingly, at infinity, you have a similar but weaker structure. Okay? And but that's it. Okay? So you have a good commutator estimate here something, and the regularity that you get will just propagate around with propagation of singularities. And this gives an extremely robust setting. It depends only on this structure I've thought. So you can perturb it, it's always the same. And this is explained by we don't really see small, big A, etc. So this we really see on the level of modes, but not on the framework. Okay. And then, of course, you have to show what is quite long. You have then to show the precise regularity of a resolvent. And if you linearize the Einstein is a little bit complicated because of all these gauge issues. But if you, so this is very similar to the talk of Dijan yesterday, I think. So if you know, for example, want to compute the first time, and you want to have a first guess of say a to the minus 1 at 0 of u, okay? And this what we in our language call, you do it by a normal operator, which is just the operator on the Minkowski space, right? Then you get the guess, and then you can compute with these terms, right? So the mode analysis, I won't really speak about the proofs, but just remember you that we can now put this linearized Kerr metric into this gauge, and that some of the gauge solutions which appear, we see at the level of mode. So this really corresponds to mode solutions, to zero mode solutions of the linearized Einstein operator, right? So these are these linearized Kerr solutions, and then these asymptotic translations, which just show up. Okay. So one might think that, so now I've spoken about linearized Einstein. Why now I speak about Tarkovsky, right? I mean, this is, well, normally you do this, we have a way around the first work on Tarkovsky and then on linearized Einstein. So at the first, so when I started about all that, I have to admit I didn't really understand the interest of Tarkovsky because you can't just do it like that, right? But if you think about the gauge issues, and they're really forced to think about it a lot, if you thinking about quantization of linearized gravity, then at some point I get a real headache, and then I discovered, but Tarkovsky already solved all that right for me. And this is why I'm now speaking about Tarkovsky. So I want to quantize linearized gravity around the Kerr black hole. Okay, and so let me very briefly remember what are the Tarkovsky equations. So now W is the y tensor, you linearize it, and you look at some particular directions. Okay, these are this Newman-Penrose tetrads. So I think about it like L and N, so these are real vectors. I think about it about like scattering directions. And N and M bar are more generators of something which is happening on the sphere. And the fantastic observation by Tarkovsky was that if I take linearized Einstein equation, then these scalars fulfill donc a scalar equation, and they are gauge invariant. Okay. There is some complication that I think one has to take seriously. These are not really scalars. They are living in a quite complicated bundle, characterized by spin weight and by boost weight. Here I've taken, so in my formulation, the spin weight is the same as the boost weight. Where comes it from? It comes from the fact that you don't want to fix your tetrad. Okay, typically what you are doing, you will choose A collinear to V plus, N collinear to V minus, and then you permit a rescaling of this and a phase for the M. Okay, so this gives you a principal bundle, and then you take your favorite representation of this action, and if you choose some particular representation, then you get this vector bundles, BSS. I will come back to this a little bit later. And then the Tarkovsky equation, right, like that, I mean, we had this the other day by Green, I think, who write this down in this way, like this a lot. So this is really the, you wrote it like that. So this is really now the connection on this GHP bundle. And you see, I mean, you have a perfect structure. You see immediately what's it with symplectic form. You see everything, right? So this is how we write down the Tarkovsky equation. So, to do, if you want to quantize a field, so on a linear level, you need decay estimates. I will argue in a moment why. It's not completely clear how much you need. This depends on the field and so on, but you need some decay estimates. So I will cite the work of my former PhD student, Pascal Millet, who does the following. So this is for all spin, can be half, and so on. So first, I will come to this a little bit later. He looks at smooth and compactly supported data. So this is reflecting what Stijan said the other day. So if you want a price law, start with compactly supported data. So, and then he looks at solutions at these equations. So I have to say here, to make this precise, that he fixes the tetrad. And this gives a bundle called B of S, where you only have the phase, which is free, and which carries a natural metric, which doesn't carry the other one. I will come to this, back to this a little bit later. And then, so when he can somehow, for this field, so this is pointwise, compute the first term. So this is a little bit better than Price's law, and this decays exactly like Price's law, you can compute it. Okay, So this is for Tucholsky. This is what we need. So some comments on that. So this is the explicit first term. And this is when there's a lot of computation with physics about hypergeometric functions and so on. You can compute it. So this, I started with C0 infinity because I need it for what is following on the quantization. But you can do it for Hn, n sufficiently large. And of course, I mean, if you have weaker conditions on the fall off of initial data, when you get weaker decay. So there's just a bunch of results on the thesis. I just wrote this one down. So this is an example of what you can get. So it's not restricted to compactly supported data. So I think the first result on that was by Dafamov-Gorniansky in 17, who gets polynomial decay in the slow rotating case. This result is more or less written for the wave equation by Peter Hinz in the full sub-extremal case. Ma and Zhang get exactly this result for very slowly rotating black holes, but only for entire spin. And then we have the result by Rita and Yakov for also the full sub-extremal case for entire spin, and they get an integrated local energy estimate. And there's a new paper by Ma and Sheftel, who get some more of its estimates for perturbations of Kerr. So this is on the classical level. And now in the time which is left, I will speak a little bit about quantization because I think it's interesting. Here we go. So you have in quantum field theory, there's a big difference between fermions and bosons. So in contrary to the classical result, I can't mix all this up. So this is only for entire spin. And so somehow the first problem that we meet is that, as I said before, this BSS bundle doesn't have any natural metric on it. Because if you read scale, and just it gives another result. So we want to do something. So this is very natural in quantum field theory. So somehow, for some reason, I don't have now, if I have time to explain it, some of the best that you can do is block 1 and block 2. But in any case, you just can't fix a tetrad and work with it. You have to keep some flexibility of a tetrad. And then we have a problem that there's no natural fiber metric or even complex conjugation. So if you take complex conjugation, then you just go to another bundle. And so the way we went out of it, and which is quite natural, we double the bundle. So this is with Christiane Klein. So we take this one, and then, so this double bundle has a distinguished metric that essentially works by duality. Okay? And this was one written then a little bit later by Schuster and Klein in a more general setting. We also double the operator. Everything is doubled. And this comes from the fact that the symplectic form naturally mixes spin S and spin minus S. And you see it, I mean, when I first looked at the Tucholsky equation, even in Schwarzschild, I mean, there's this photon sphere. And then at one side of the photon sphere, it looks like pumping energy. And on the other side, like damping, say for spin S and for spin minus S, it's the other way around. So it's very natural to try to mix this together. So you double the operator, and then it's formally self-adjoint or Hermitian and green hyperbolic, meaning that you can solve the forward and the backward forcing problem. So this is the problem we saw the other day. So this is, you look at TS, Phi equals F. F is somehow, say, compactly supported to make it easy. And then you look at the forward or the backward solution of this. Okay, there's a whole field around it, and you can do it. And this enters there. And then you have this very, where you have been speaking about, this very important symplectic form, which is here essential. And so so perhaps we can discuss this a little bit later, but for some reason, so with all quantum field theory is usually based on what is called space compact solutions, meaning you take a slice, then your support is compact. And this has to do with some properties of the algebras that you want to construct, that if they classically don't see the fields each other, when the operators have to commute, something like that. Okay, so this is perhaps not optimal for linearized gravity, but this is just for that for the moment. So let me speak a little bit about the algebra. So this is called CCR algebras, which are the algebras for bosons. So you start very primitively. You take unit element in some field, and you multiply addition, everything what you want to do formally. You just write it down. But then to make it interesting, you have to quotient by some relations, and these are these relations. You want that your field, capital phi, has a linear dependence on your field, small phi, and the other one is, so this is, no, sorry. So this is antilinear and this is linear. If you take the dual, then you get the other field. And the most important one is this one. This is the canonical commutation relations, which translates a lot of physical properties of bosons. For fermions, you would have what is called canonical anti-commutation relations. Okay. We will see in a moment, if we do this very naively, we get an algebra which is far too large. Okay, I will come to this a little bit later. And the state, so ask questions. I mean, probably a few of you are only used to quantum field theory, so don't hesitate. So a state is a function on the algebra which goes to C, which is normalized. So the state on unity is 1, and omega of A star A is positive. This is a very important condition with positivity of the states. And this is the reason we will see it in a moment why this algebra we start with is too big. And then, so one thing that you can do is to take this phi star of psi, phi of phi, so this is not optimized for our presentation, but we'll see what it is, right? And there are states which are called quasi-free, which are completely determined by this one. Okay, and now you see that you just have a sesquilinear form on your fields. Okay, somehow, very, very soon we can forget about the algebra. So this is just a sesquilinear form on the fields. Okay, this has to be positive, and the commutator relations just translate by this. Okay, you see in the commutator. So this is very important here. So this brings in the symplectic form. So boson theory is really based on a symplectic form, where fermion theory is based on the Hilbert space product, right? And then something I won't really speak about, but which is very important, which has something a big issue, is now somehow you can take these functions on your right-hand side, and this become distributions. And these distributions have to have their wavefront set in a prescribed positive energy shell. So this is from a physical point of view, this is very important. If you go from Minkowski spacetime to something like Kerr, you lose your symmetries. Okay, Minkowski spacetime, what is the vacuum state in Minkowski spacetime? It's just a state which is invariant with respect to the whole Poincare group. This you lose here, and this is replaced by this kind of micro-local conditions, but I won't speak about it. So, okay. But this is a big issue. So what we obtained with Christiane Klein is what is called the Unruh state for Tucholsky. So the theorem says that essentially we can build up what is called the Unruh state in block 1, block 2. It fulfills this Hadamard condition, and it is positive. Okay, let me a little bit describe the idea of what is an Unruh state. If you want to define this kind of states, essentially it is choosing positive and negative frequencies. If you look at this, so this is your future horizon, this is the past horizon, this is chi plus, this is chi minus. Here at chi minus, you have a very natural killing vector field, which is just dt. On the horizon, it's more tricky. You could first try. You have dt plus omega d phi, which is the same somehow, you just rotate with a black hole. It turns out that if you do this, you remain restricted to this exterior. Okay. So what UNO did is 1 plus of the capital U. Capital U is the Kuskai coordinate. And then something funny is happening. So this is now a one-dimensional analysis. You can take dx as an operator of R to A2 of R. And then you can compute 1 plus of dx as a bounded operator from A2 of R to A2 of R. But you can also look at it as A2 of R plus to A2 of R plus. Okay. And if you do it like that, then this is an exercise in Fourier analysis. This is some function of a generator of dilations. And this function is encoding what is called the Hawking temperature. The Hawking temperature is just based on this computation. So this is, because this is more or less up to a constant, this one, if you take the Kuskai coordinate. So this is where, so if you ever heard about Hawking temperature, this is just this exercise, how it comes in. Okay, so let me, before explaining how this works, let me be some remarks. This has been quite of an issue for a long time. So there are no-go theorems by Kay and Wald and Pinamonti, Sanders and Fersch, which say essentially the following thing: if you take a killing vector field, which is not globally time-like, and you do this kind of construction, then it can't be Hadamard. And the idea here is scattering. So what you have to do really is to separate your solution to one part which goes to horizon and one part which goes to null infinity with the scattering, and then you just choose different vector fields. Okay, that it is. So it's not really constructed like this was supposed in this theorems with respect to a single killing vector field, but to several, but you have to split the algebra. Okay, and then there's a story about that, Piace, Moretti, Pinamonti, myself, with Christian Gerard, Michel Broschner, and Klein. And another interesting aspect of it is, so this kind of state, what is called the UNO state, is really the state that you get if you look at the collapse of a star collapsing to a black hole, when it converges to this kind of state. And this can be done, so this was predicted by Hawking, can be done mathematically, first by Bachelot and then by myself for the Kerr case. So I just want to try to understand how to construct the physical space. So what is, if you look just at solutions of the Tucholsky equation, phi s and phi minus s, when it's too big, you don't get positivity. So let me explain why it is too big and how you can construct it. You start, and this is really classical Tucholsky equation, you start with a Hertz potential, solution of T minus phi minus equals to 0. And then what is happening, so this is, if you take some GHP derivative, so this is linked to the Tucholsky-Starobinsky identities of this, then you get the solution of the other equation, the first observation. And you also have some angular Tucholsky-Starobinsky identities. So these are also operators that you can write down in this GHP formalism, but which are purely angular. Okay, so what we really do is the following: take and then in the end, so let me say it like that. In the end, you get a relation between phi minus and phi s. Okay, so with this operator bs, so it goes like that, and so the physical space are solutions which are linked by this kind of identities. The idea is you start with a Hertz potential, go back by some reconstruction scheme of the metric to the metric, construct the other Tolkowski scala, and then you get this kind of relation, which is the good one. Okay, so the phi minus s is not the Hertz potential, but for some technical reasons, this operator applied to the Hertz potential. And then it is, my time is almost over. It's a boundary to biconstruction. So what you see here, so this x plus, this is exactly what I've written here, just the spectral one characteristic function of this. And now, because of the Tolkowski-Starobinsky identities, these are essentially null derivatives along the horizon or along null infinity. So we can play around, and so this gives the positive expression. Okay, so this is, and these are trace operators, so we have to take the traces at infinity, of course, this is kind of conformal trace. And this is the good definition of a Unruh state. It's positive if it's a Hadamard condition, everything that you want. Thank you.
Thank you very much, Peter. Are there any questions?
Yeah.
You have the alpha have low bound, right?
Sorry?
You have alpha, the index alpha.
Index alpha. So this is the decay for the linearized Kerr. Okay, yeah. So alpha is between 0 and 1.
Yes, but you have another next slide. You have this low bound. Yes.
So this is the work of Anderson, Blue, and Ma and Bechdel. So they need alpha a little bit larger to make the analysis work. And so this, as far as I understand, kicks out the linearized Kerr solution, but still.
This is sharp or not? The 502 is sharp or not?
I don't think so. No, it's sharp. So this is rather a question for Peter than for me. I mean